license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
And I think we're about ready to get started. So welcome, folks, for lecture number 2 of Fundamentals of Photovoltaics, focused on the solar resource. What I wanted to do to get everybody in the mood of thinking about the sun is pass around a few balls. So this is really A, to limber you all up, but B, whoop, there we go. All right, don't let it fall. There you go. I know Ashley's got solid hands. All right, here's one. Pass that around as well. We've got a few more. There, and lastly, right up the middle. There you go. Okay, so today's lecture is really about the solar resource, and as we go through, it kind of helps to have a sphere in your hands, since oftentimes we perceive the world as being flat, no fault of our own. Locally, one can approximate it as a flat body. That's certainly a good possibility. Wouldn't mind passing these out to your friends as well. Thanks. But in reality, if we really want to understand the solar resource, we really have to begin understanding or thinking in terms of spheres and in terms of circles, or in most cases, ellipses. And so we're going to dive into the solar resource. Before we really dive in detail into the solar resource, I wanted to give you feedback to your surveys. So you did a background assessment survey, a census, if you will, and filled out a number of questions last class about your backgrounds. And I wanted to provide you the feedback, the consolidated information, because it's really telling about who your colleagues are. This right here is a little bit of a snapshot of expertise and current career trajectory. So the self-defined expertise in the bottom left is really, I think, the most telling parameter. For the undergrads here, you may define yourself by your major today, but when you graduate and go on to grad school, you might, say, for example, do your undergrad in physics and then do your graduate school in mechanical engineering, but still consider yourself a physicist at heart. And so that's why I ask this question here: what is your self-defined expertise? Because there are several graduate students who have changed fields, if you will, from undergrad to graduate school. Most people in the audience, by and large, consider themselves engineers, either material science engineers or mechanical engineers. Chemistry is strong as well. And then we have about 10 different departments here represented. And that's really cool. It's going to manifest itself in the class projects. And you'll see the diversity of different inputs and perspectives from your colleagues. The degree in progress, undergrad, grad, is about split 1/3, 2/3, grad and undergrad and grad. ASP is advanced studies programs. So these are folks coming in from industry who are actually here in the classroom. Some of your colleagues in the class are folks who are in industry and perhaps have real-world PV experience. Several of the people here in the class as well have either have gained expertise in solar with their hobbies, with their work. Some have installed solar panels. Other ones have done research or are doing research in solar. So it's a pretty diverse group. And some are as well members of the solar car team, which is rolling out its new model in a few days' time. In terms of learning methods, it was pretty well split between hands-on labs, field trips, and guest lectures. And I'll get back to that in a few slides. In terms of class project interest, there was a strong interest in working with pre-established projects. So we've listened to that. This is pretty consistent with previous years. And so we have several pre-prepared class projects ready for you. And a few of you had an interest in the self-design project. I'd like to talk to you. I'd like to begin developing those ideas as soon as possible so that when we start assembling teams, if you do have a strong idea for a class project, we can begin crafting that and molding that starting now. So please come up and have a chat with me after class or during office hours or during recitation. These are your learning objectives defined by you. And they range, I tried to give it some continuum spectrum from natural sciences to social sciences and engineering in the middle. And obviously this is more of a loop than a linear line, but bear with me. There was a strong interest in fundamentals, and that's certainly, I think, what the core of the class is about, at least the first third of the class. Going in terms of size of the bubble, these are the number of people who listed a particular topic as of great interest to them. Economics and market, systems and grid, current technologies, emerging technologies. And so listening to all of this, we are in the process of preparing for you some guest lectures and field trips based on this feedback right here. We have already the solar resource, the sun. This is where it all starts. If we're to understand PV photovoltaics, the conversion of sunlight into electricity, it starts from the sun. And so spending some good time thinking about the sun is really, really important. And it will avoid the embarrassing situation. How many of you have been at a shopping center walking along and a little child is asking his parent, Dad, why is the sky blue? Or why is the such and such? And the answers you'll hear just make you want to tear your ears out. And say, my goodness. So solar resource maps, in other words, how much sunlight is available. And we want to be able to estimate a solar resource amount locally at a specific spot on the planet. We want to list the causes of variation and intermittency of the solar resource and quantify their time constant and magnitude. In other words, we want to be able to discern what are the big effects and what are the ones that don't really matter. We want to be able to estimate the land area needed to provide sufficient solar resource for a project, whether it's a house, a car, a village, a country, a world. And a lot of this will be on your homework assignment. So we'll give you the tools here, but then ask you to address those questions. And for those of you who have already picked up your piece at number 1, you'll see relevant questions. Where's this? Does anybody recognize this right here? If I start rambling off names. What city has Pennsylvania Avenue, Independence Ave, Washington, D.C.? This is right outside of the National Air and Space Museum. What this little girl here is pointing to is the sun. And then we have Mercury, Venus, Earth, Mars, and so forth. So it's essentially a solar system to scale. As you walk out of the Air and Space Museum and walk down the street, you'll be passing the different bodies in our solar system. And so just as a quick little review to kind of get us situated and to ask the questions that little kiddies might ask us, how far is it from the Earth to the sun? About 100 million miles, yeah, 93 million miles. Plus or minus somewhere in the range of maybe a percent or so, a few percent, depending on what time of year we are, since we're in a little bit of an elliptical orbit. Good, so that's the distance to the sun. It would be about 150 million kilometers. How long does it take light to travel that distance? About 8 minutes, 8 1/3 minutes, right? So it takes a little bit for the light to reach us. Good. Some more questions. How far are the other planets in our solar system to the sun? Just going in order from Mercury out. Just to get us situated here. If we are at any point planning on throwing up satellites and sending them to other planets, this is a good thing to kind of keep in the back of our minds. So if we define an astronomical unit, not in terms of our national debt, but in terms of the distance from the Earth to the sun, that's an astronomical unit. Mercury would be somewhere around 0.4, Venus 0.7, Mars 1.5, so that's all kind of in our neighborhood, right? And then from Mars to Jupiter, there's a bit of a jump. It goes from 1.5 to 5. And then from Jupiter to Saturn is 10. Well, sorry, 10 is the distance from Saturn to the sun. And then 30 and then 40. Sorry, 10, 20, 30, 40. So it goes, Jupiter is 5, Saturn 10, Uranus would be 20, Neptune 30, Pluto 40, right? Pluto, planet, sort of. So it's easy to remember those numbers because it goes 5, 10, 20. That's just essentially a sequence of doubling, and then 10, 20, 30, 40. I'm giving you approximate numbers here, but that's something just to keep in mind, all in terms of astronomical units. So in case a little kid comes up and asks you, you can spread out the answer. Let's talk about the sun. This is just a review of our readings right here. This was a representation of the sun and the Earth moving around. And what is solstice and equinox? What do those refer to? What is the equinox? Yeah, equal amount of light and dark throughout pretty much all the world, except if you're really standing on the tippy top in the bottom. So equal amount of light and dark throughout the world on that particular day. So the day and the night have the same amount of length. If you move over into this region right here, this would be a region of our northern hemisphere summer, southern hemisphere winter. Over here, vice versa. And the solstice would be? Yeah, so the shortest or the longest day of the year, depending on what side you're on. So in the northern hemisphere, the June solstice would be the summer solstice. For us, it would be the longest day. And if you're in the southern hemisphere, it would be the shortest day. Depending on what time zone you're in, there might be a variation of one day hitherto. Good, okay. And what is this, what are the seasons caused by? What is this kind of tilt right here? What is that called? Declination angle. And approximately how much is that? 23.5, 23.45, yeah, so 23.5 degrees, good. Okay, and we can visualize all of this on the PPCD-ROM on the website. So this was part of your signed reading, and here's the Earth going around the sun in this representation. Likewise, if you want to take one of your balls and just kind of imagine being on one of those surfaces, you see the diurnal rotation here, it's spinning around its axis, and as well the seasonal variation as it spins around the sun. That's important for a number of reasons, right? That will determine how much sunlight is normally incident on the planet. If you are normally incident, if you're at this exact spot right here, you're receiving the sunlight full on. But if you're up here somewhere, right, your surface normal is pointing, some vector pointing out like that, you're only going to be receiving the cosine theta of that amount of sun. Right? So if you're an extreme example, if you're right here, you're not going to get any. But if you're in this part right here, you're going to get cosine of 0, which would be 1, so you get the full amount of sun. And likewise, as you move through the angles here. So it's important to understand what the relative angle is between our surface normal and the vector pointing at the sun. That varies as a function of season. It varies as a function of time of day. And obviously, over the entire Earth, you can define the precise amount of sunlight coming in, the precise solar resource, by a series of trig formulae. It gets pretty complex, and this website will actually walk you through it if you're so interested. Now, this is all review, since folks have all done the background reading, right? All done the background reading. Expect you to before class. Let me ask you a few trickier questions just to see if our creative juices are really moving at this early time of day. When would be the shortest day of the year? Let's start there. The shortest day of the year is approximately December 22nd, right, in the solstice. When is the latest sunrise? And when is the earliest sunset? You might need to pick up your little ball and rotate it around. Does anybody have just a gut sense? Would it be on the solstice? How many people think it's going to be exactly on the solstice? Let's say earliest sunset. How many people think that the earliest sunset is going to be a little bit before the solstice? How many people think a little bit after the solstice? I know people don't really know. The reality is that the earliest sunset would be a little bit before the solstice here. And the latest sunrise would be a little bit after the solstice. And it flips in summertime. It would be, let's see, the earliest sunrise and the latest sunset, yeah, before and after the solstice, respectively. Okay? And you can kind of think about that in terms of what is the solar noon. The solar noon is when the sun is directly overhead relative to our chronological noon, which is, I would say, less dependent on the specific angle of the Earth relative to the sun as it moves around this trajectory. Let's get more into that in recitation. I sense since there wasn't much traction there, I don't want to dwell. Okay. Good. Okay. Let's think a little bit more in terms of the trajectory of the sun later on as we move through some of the introductory material. I don't want to dwell too much. I want to give a little bit of review since I'm sensing that not everybody did the readings. I expect you to do the readings, folks. So let's keep with me here. So a touch of history, since that was asked for, it was requested. I decided to launch a little bit into a history of the study of the sun. Philosophers going back to what I suppose most would consider early India studied the sun. There were some writings of some of the earlier philosophers that were recorded. Some have interpreted these writings as being indicative of perhaps heliocentric models. These are poetry, folks. It's a very different style of communication than what we have today of technical writing. So it's difficult for us to discern, or difficult for me at least to discern when I read the lines verbatim, if this is really somebody thinking about the heliocentric model, or whether this is somebody just describing the universe in the best of their abilities. The real beginnings of heliocentric models began in the 3rd century before the Common Era, and the notions of interstellar distances estimated in a similar manner to what we just walked through today, right? Estimating the distance between the Earth and the Sun and then using that as a measure or a yardstick with which to measure the distances to the other planets began somewhere during that time. Likewise, these writings of old made their way to the Middle East. And in the 10th and 11th centuries of the Common Era, the Middle East, the Arab world was really where science and technology was at. And these days, Europe was still largely mild in the Middle Ages, starting to emerge but in a few places. But by and large, the carriers of civilization in the Western world were really centered in some of the Arab cities in the Middle East. And Al-Biruni in particular was very avid at applying methods of astronomical observation, in particular to aid travel, but in the process discovering a thing or two about our known universe. And of course, finally, Johannes Kepler in Europe, once it starts to emerge from the Middle Ages, with really taking observations from other scientists who very carefully plotted out the position of the different bodies. He came up with some of the mathematical models that described the motion of the planets through the skies, and is largely credited with developing a series of laws that define interplanetary motion. So a couple of interesting things to note is that international collaboration was really essential. These ideas didn't develop in isolation. They were flowing throughout the world. It's important to know that many of the scientists were well-traveled polyglots, meaning they spoke different languages, and that's how they were able to interpret the texts and readings of other people. And it's also to note that parallel astronomical developments were happening in other regions of the world, the Far East, Mesoamerica, and so forth, right? And so obviously there may have been some communication, I would say rather sparse between, especially with the Far East, but there was a fair amount of communication between these regions here, and you can imagine writings or ideas traveling from word of mouth along trade routes. So there was some communication. So back to our learning objectives. Today we're about to quantify the available solar resource relative to human energy needs and other fuel sources. So let's do that. We'll jump right into one of the slides that I showed you last time. This is in terms of terawatts AV. Terawatts is a unit of power, very big one. Tera is 10 to the 12. And you can see here the resource of the sun relative to the wind energy resource base relative to human energy needs. If we just consider the resource falling on the Earth's surface as opposed to that falling in the outer atmosphere, there's a little bit of a discount, but we're still very large compared to human energy use. And if we redefine our units from terawatts into HECs, which are human energy consumptions defined in, say, 2050, where 1 HEC is the average, let's say, energy burn rate of 2050, you can see here that these numbers are a few orders of magnitude larger than what our human energy needs are. So if we were able to capture only 1% of all of the solar resource falling on the Earth's crust, we would be actually in pretty good shape. And 1% of the total land area on the Earth's crust, I believe somewhere between 1 and 2% of the United States is covered in asphalt right now for roads. So this could be on houses, on rooftops, and buildings, and so forth. We wouldn't necessarily have to exclusively repave virgin farmland with solar panels. So going back to quantifying the solar power, we have our sun. We're going to start by quantifying the solar resource by assuming that the sun is a black body. The same way that hot objects emit light, say for example when you turn up your stove and you have a very warm glow coming out of it, the sun is as well a hot body, a black body, sorry, very hot as well, somewhere around 6,000 Kelvin. And the total radiated power is given by Stefan Boltzmann's law here in the following way, where we have temperature to the fourth, and the temperature is somewhere around 6,000 Kelvin. And so we have this power being radiated out at the surface of the sun, and then as it travels outward, it becomes, you could say, diluted in effect, because the total surface area of that sphere is increasing, obviously as r squared. And so by the time that that light reaches the Earth, it's only a very small cross-section, or a very small solid angle, to be more precise, of the sun's surface that is radiating directly at the Earth right here. Because this in the absence of scattering centers in the universe that might reflect or bounce the light back toward the Earth. And you can calculate the total power incident on the Earth by that simple formula right there. What is the radius of the Earth? Again, one of these simple numbers you should kind of have in your head. 6,370 kilometers, somewhere in that order, right? And so you can begin estimating here the total power on the order of magnitude. It's going to be tiny compared to the total power that the sun is radiating, thankfully, or else we'd be pretty hot right now. So the average power coming from the sun on the surface of the outer atmosphere is around 1366 watts per square meter. Who's heard of 1366 before? Yeah, you've heard about it? All right. You know where the number comes from now. All right, it's pretty wonky. 1366 is a startup company, a spin-off of MIT focused on solar energy. OK, and so that's at the equinox, which we just learned is occurring somewhere around March 21st, September 21st, coming up soon. Celebration. The ratio of the surface areas of the spheres is really something to keep in mind right there. OK. So we've quantified the available resource relative to human energy needs. Now we have to come up with some language that we use to describe the sunlight moving through the atmosphere of the Earth and reaching the surface of the Earth, right? So we're going to use what's called the air mass convention, or AM convention. AM stands for air mass. Even without knowing much about how the light is absorbed or how to quantify it mathematically, we can assume that our atmosphere contains molecules, it contains particulate matter, and that's going to interact with the light in some way. It's probably going to either absorb or scatter it. And so as the light passes through our atmosphere, there's going to be some absorption. And the greater the distance, the greater the optical path length through the atmosphere, the more absorption and more scattering there will be. And so we use air mass, or AM convention, to define the path length or the path distance through the atmosphere. AM0 would mean the outer atmosphere. AM1 would be essentially just going straight through normal incidence, so that the direction of the trajectory of the light is parallel to the surface normal of the Earth at that location. And then air mass 1.5 and so forth is as we increase the angle of the entry of light relative to the surface normal. So in other words, as we go further from the equator to northern latitudes, that air mass number is going to go up, up, up. OK, we'll explain it with a few graphs and figures in a few slides. So we have our atmospheric absorption. When you just glance at the Earth and these beautiful pictures taken from outer space, we can see very obviously the clouds present. And more importantly, if we were to zoom in on one of these regions right here, we would see this bluish hue coming from our atmosphere, which is scattering preferentially the shorter wavelengths of light. And more importantly, this radius right here is somewhere in the order of 6,370 kilometers. And this thin atmospheric shell is in the order of 30. Right? So that's why you don't really see too much of a ring around the planet from this distance. So atmospheric effects, let's try to bin them into discrete buckets. This is a simplification, but it helps us gain a foothold in understanding. And then from there, we can make our understanding a bit more complex. So we have incoming solar radiation coming from here. We have a number now that's 342 watts per square meter. Why is that number so much lower than the 1366 that we were just talking about? Yeah, so this is meant to be an average over the entire day, at one fixed point along the ground, right? So as we're rotating around, we have at least half of the day normally when we don't have sunlight. And then there's, I would say the cosine theta angle is not 1 at all times. It's very rarely 1. And so this is a bit of a discounted incoming solar radiation, essentially a time average solar radiation for a given patch of the planet over a typical day. And so we have a variety of processes here. We have reflection off of clouds. That's pretty clear to see from here. Looks nice and white. We have some absorbed by the atmosphere, typically in rotational or vibrational modes of molecules up in the outer atmosphere, sometimes by particulate matter as well. And then we have the amount that's absorbed here by the surface, of course, reflected as well. And so the amount that's incident on the surface or coming down to us is what we can actually use to make solar energy. And this is an average, right? Because sometimes the cloud cover is a lot greater. And for that particular day, we will have a lot less resource striking the ground at that given time. This over here, this is all mostly infrared, right? Where this is visible coming in, once the light gets absorbed and then gets re-emitted, usually gets re-emitted in a longer wavelength light, or the infrared light. And this is the stuff that gets blocked by or absorbed by greenhouse gases and then re-emitted equiangularly, and some of it makes its way back to the Earth. Right? Okay, so air mass. Let's define that so that we have a common language that we can use to describe the solar resource from place to place. So again, this is the sun. This is the surface right here. And let's imagine that the angle between the incident sunlight and the surface normal is 0, such that the cosine theta term is 1. Air mass here at this point on the surface of the Earth is going to be AM1. So we call air mass 1 if the sun is literally directly overhead. What did we learn about the declination angle of the Earth? It's about 23.5 degrees, right? How far north are we? What is our latitude here in Boston? 41, 42-ish, right? So let's, for simplicity, say that here in Boston, our latitude of Boston Logan Airport is approximately 41 degrees north. And let's say that the declination of our planet is approximately 23.5 degrees. Right. So what would be the angle of the sun in the sky if you were to lie on your back in the middle of the summer solstice and the middle of the winter solstice, and you're lying straight on your back looking up at solar noon? What would the angle of the sun in the sky be relative to the surface normal? How far south would the sun be? Imagine that this is 0 degrees and that's 90, right? So relative to this angle right here, where would the sun be in the sky? Why don't you turn to your neighbor right now and discuss. On the summer solstice, the winter solstice, come up with some set of angles there. All right, folks, what did we come up with? This is our little human being, you, in Boston. This is south, and that's north. And we're at the solar noon in the winter solstice and the summer solstice. So here's you. This is directly above. So let's say if you're lying on your back and looking straight up, that's the surface normal of the Earth. In the summer, at solar noon, the sun would be at what angle relative to the surface normal of the Earth? 17.5, somewhere around there. And how did you get that number? Subtract those two, right? So you get 41 minus 23.5. You're somewhere around 17, 18, somewhere around there. So we'll call it 18 degrees in summer, again, relative to the surface normal. And in wintertime, what does that work out to be? 64.5. Similar logic, right? So we'll call it 65 degrees in winter. Good. So what does that work out to be in terms of air mass for winter and summer? Quick engineering approximation, I'm going to say that in summer it's approximately air mass 1, but you can calculate it real quick. Somebody with a calculator want to plug those in? And roughly 2 in winter, right? Okay. We're going to get into scattering of light in next lecture, actually, and we'll see why that matters in terms, especially of getting sunburned, since the shorter wavelengths, the ultraviolet, are more sensitive to the path length. Okay. Good, very good. So we have pretty much a gut sense now of where the sun is in the sky. And as it moves from summer to winter, from our perspective, it follows a little bit of I would say a sinusoidal path, right? It stays in summer for a long period of time up here, and then it moves pretty quickly down here and then stays here. So versus time, the angle of the sun in the sky is following a sine curve, or cosine curve, if you will, right? And so right now, the sun is actually close to the middle. We're on September 13th. The solstice is coming up in a week's time. And so the slope of that sine curve is at a maximum right about now. And so the amount of time that the day will change in length is changing at its greatest point right now in the year. And so you really begin to notice it if you start paying attention. Or if you go to weather.com and start looking up how long is today's day going to last? When is the sunset tomorrow? I don't know about you folks, but I like to cycle. And when I'm doing my evening rides, I'm noticing it now. that I have to start earlier and earlier if I want to put in, say, 30 or 40 miles. I'm not going to be able to make it home in time. So, so that's the sun and how it relates to you in your daily lives. We're going to get back to this in a minute, so keep this in mind. Don't let it out of your RAM. Let's talk about the actual solar spectrum for a minute. This is the sunlight intensity in some very weird units. We'll get to that in a minute. But think of this in terms sort of like the total amount of power in a given bandwidth. So the wavelength right here, or the power density in a bandwidth, the wavelength is the wavelength of light. Shown for your convenience here is the visible spectrum. That's what our eye, mostly what our eye is able to detect in this wavelength range right here. And the sun is emitting over a much broader range of wavelengths. It's emitting following a black body emission source at 6,000 Kelvin. In essence, this very difficult to see green line right there. Air mass 0 spectrum looks like this red line right here. And again, letting me remind you that the air mass 0 is the light that's falling in the outer atmosphere. There is no Earth atmospheric absorption yet. Why do we have these little lines here? You see, it's not a perfect black body. We have some, I'll give you a hint, absorption lines. Where is that light being absorbed? Is it the ether between the Earth and the sun? No, there's no ether between the Earth and the sun. Where's that light being absorbed?
Hydrogen ions and stuff.
In the sun itself, right? So these are absorption events occurring in the solar atmosphere. And now, if we do air mass 1 or 1.5, let's push it up a little bit from air mass 0. This is now passing through an angle somewhere around 60 degrees. Now, what do we have? We have several absorption lines occurring, right? And these correspond to absorption events where? In the Earth's atmosphere, exactly. And so we can attribute each of these little absorption lines here to a particular, usually it's a molecule, in the Earth's atmosphere. Note the sensitivity of the human eye in black right here, and how well matched it is to the air mass 1, air mass 1.5 spectrum. That's pretty cool. That's pretty cool. Okay, so, so there you have the spectrum. Let's get to these units of power density per bandwidth for a second. The way to think about those units is as follows. Kilowatts per meter squared. Okay, I get that. It's the amount of power falling on a unit area. Per micron. The reason it's normalized per micron is because the wavelength units right here is in microns, and if you take the product of the two, it makes it pretty easy to calculate the total power density, right? So if you want to calculate the power density, the total watts per square meter falling on the Earth, say between 0.5 and 1 micron, you can calculate the total amount of power by multiplying one versus the other. So that's why they're in this weird unit right here. It's to help you perform calculations, like the ones you'll do in your homework, like the ones you'll do for your class project, and so forth. And it strikes a little bit odd the first time you look at it, but it begins making sense, and you're appreciative of it after a while. There are standard spectra. There are standard reference spectra. Sure, you can go outside and using some form of spectrophotometer, you can measure the incident solar radiation and map out the spectral irradiance as a function of wavelength. In terms of planning or communicating with other scientists, we typically refer to standards. We use common yardsticks, common metrics, and that facilitates communication, avoids ambiguity, avoids misunderstanding. And so these standards right here, these ASTMs, refer to the particular standards that are used for those solar spectra. And in your supporting online material, at the very end of the lecture slides online, we go into some more detail regarding that for those who are interested. So again, these little absorption lines here correspond to specific atmospheric events, interactions of that particular wavelength of light with some molecule usually in the atmosphere. We can as well have generalized attenuation due to other scattering mechanisms. Notice right here in the short wavelengths what's happening. From the red to the blue, this light is particularly affected. We have a sharp drop in the shorter wavelengths, and it grows sharper the shorter in wavelength you go. So the attenuation, due to passing through the atmosphere, grows or increases the shorter in wavelength you go. And this is a process generally called Rayleigh scattering, and there is a wavelength to the fourth dependence. So as you go shorter and shorter in wavelength, the likelihood or probability of scattering will increase. Why is that pertinent to us? Well, now you can answer that little child who walks up to you in the shopping mall and says, why is the sky blue? You say, well, there is this elastic scattering mechanism of electromagnetic radiation, whereby in a broad spectral event, such as the sun, black body emission, we have the shorter wavelengths that are scattered more, and that's why when we look away from the sun, in the other direction, we see those shorter wavelengths that are scattered back to us. That is pertinent for two reasons. A, it makes the sky look blue. Secondly, it's not only the short wavelengths in blue light that we're worried about, but also the ultraviolet radiation, right? So even on a cloudy day, if there is a few open patches and you can get scattered light coming in, you can still get sunburn. And secondly, there is a very strong dependence on the path length, the optical path length, the air mass, right? So if you go further north in latitudes, where your air mass increases, right? Because now, if you think about the atmosphere as being kind of a flat, just give me an approximation for a minute. If you think of the Earth being flat and the atmosphere being flat, now the path length in winter is much, much greater than the path length in summer. Same sun, just different path length. You're much more likely to get sunburn in summer than you are in winter, because the path length is a lot shorter, and the amount of short wavelength ultraviolet radiation that will be scattered away is going to be less in the summer than in winter. That's also why if you go south in latitude, for example, from here, say to Miami, your incidence of getting sunburn is a lot greater, a lot more than the total increase of the visible portion of the spectrum. So the sun might not look that different to you, but your incidence of sunburn events goes up quite a bit, and that is due to Rayleigh scattering. And now, by this point, the little child has already run crying back to the parent. But you have a full satisfaction of knowing how the universe around you is put together. And that actually was a pretty deep problem. It took a long time for at least European scientists to crack that nut and figure out what was going on. Describe how solar installation maps are made and use them to estimate the local solar resource. So we have metrology. We have techniques that we can use to measure the amount of sunlight that is out there. And now we want to apply those in some systematic fashion to measure the average solar resource around the planet, including the oceans, and then use that information to estimate later on the land area needed, or the size of the array, or how many cells we're going to have to string together based on the solar resource locally. So how are these insolation maps made, these maps that we'll use as engineers to size our systems? First off, let me define insolation. This is not insulation, as in stuff you put around the house to keep the heat from going out. This is insolation with an O, a shorthand for incoming solar radiation, insolation at the top there. It's typically given in units of energy per unit area per unit time. So kilowatt hours, that's energy, per meter squared per day. And it's helpful when designing or projecting these PV systems. And it's affected by a bunch of stuff, which we'll get to over the next few slides. So we can measure insolation from the ground. That's a surefire way to do it. This right here is a pyranometer. Pyro, fire, sun. Ano, on top of, right? So anode, cathode, kata, under, ana, above, catatonic, under, right? Okay, so pyranometer, so it's basically measuring the sun above, right? It's measuring the sunlight above. This is a full hemisphere, measuring the sunlight coming in from all angles. There's a small little sensor right here. It's lying flat, and that glass is essentially allowing the light from different angles to get in to the sensor. And this is a very narrow, solid angle of the sky. It's probably just looking at the sun, or in a particular direction rather, plus or minus 2.5 degrees in either direction. So it's a very limited solid angle of the sky. This one over here would be more appropriate, say, for a flat panel that's receiving scattered light coming in at all angles. This one over here would be more appropriate for a tracking system, especially a concentrator system that has optics that only accept light in from a very limited solid angle. So imagine you have a lens that has to have light incident to it to focus it on the right spot. And if the sun moves in the wrong spot, or put it another way, if the lens is in the wrong position relative to the incident solar radiation, the light is being focused off of the solar cell, and it doesn't produce any power. So this is a system that's used for measuring the direct solar spectrum, which will be useful for calculating the total output from concentrator systems. And this pyranometer over here is useful for flat panel systems. And we can also measure the total amount of incident solar radiation, total amount of insolation from the sky using satellite imagery. This is an example of a measurement. And this right here is insolation, average insolation from 0 to 550 watts per square meter, taken from a NASA satellite with the NASA Earth Observatory. Very cool website, great place to spend a Friday night if you don't have plans. Just log on here and bunches of maps from snow cover to population density to CO2 being emitted to wildfires around the planet. Anything that a satellite can measure, they're measuring, and the insolation value is one of them. And so we have data from various points. This is the insolation in January. So in January, it's the southern hemisphere's summer, the northern hemisphere's winter, and as a result, we have less insolation up north. We're in the blues. In the southern hemisphere is more in the reds. And of course, the tide turns. In July, we have our summer, and the southern hemisphere has their winter, and the poor folks here in Antarctica have nothing. So a couple of things to note, just already straight off the bat. We're noticing that there's, in general, higher insolation near the equator passing right through here, right, approximately. Fun fact, small city up there in the north of Brazil, there's a soccer field that is half in the north and half in the south. Anyway, that's neither here nor there. We have rainforests up here in the north of Brazil, Central Africa, and here in Southeast Asia. And even when the sun is directly overhead, those clouds are preventing some of the sunlight from getting in. And that's why right at the equator itself, we typically have less insolation than we do in the tropics, say Tropic of Capricorn, Tropic of Cancer. Tropic of Capricorn running straight through Sao Paulo, Brazil, Tropic of Cancer running through Key West, just to situate yourselves. And the tropics are how far away from the equator? Right, okay, 23 and a half, good guess. Good, so what we're going to do is now launch into our next learning objective, which is to list the causes of variation and intermittency of the solar resource and quantify their time constants and magnitudes. This is really, 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 really important. The other stuff is very useful from an engineering point of view, from answering certain questions in your homework. This right here determines, or is the singular reason, one of the singular reasons why solar doesn't behave like a regular fossil fuel source, why solar does not produce power all the time. It is variable in terms of its power output. Variability generally refers to the fact that we can predict it's coming. It's going to vary, but at least we can predict it's coming. Intermittency, while not a strict definition, the understanding when somebody says intermittency or intermittent power source, the impression that it gives is that it's unpredictable in terms of its variability, in its variation. So we've talked a little bit about the variation so far, and about the predictable nature of the sun. We've talked about how the sunlight, the solar resource, varies from summer to winter. We've talked about how the solar resource varies as a function of latitude, right? But now we're going to talk not only in a little bit more depth about that and have a few fun in-class exercises to get us really grasping that concept in its entirety, but also talk about some sources of intermittency, which if you have a large amount of solar contributing to the grid and it is intermittent and you have no way of dealing with that, you're going to have fluctuations of energy level on the grid or power levels here as a function of time, and that's not going to be good. So in terms of the seasonal variations, in terms of predicting the amount coming from the sun at a given point, I told you it looks a little bit like a sine or cosine wave, and indeed it does. You can calculate those values based on this website right here, just to show you how nifty and cool it is. Our friends at Arizona State University, Stuart Bowden and Christiana Hansberg, really put in a lot of time to make this. You can vary the time or the day of year right here, for instance, right? And you can see how the solar resource, this is the direct radiation, kilowatts per meter squared, and this is the time. So if you take the integral of the curve right here, you're going to get what? Units of? Power times time is energy. Energy per unit area, right? So you're going to be able to calculate the total amount of energy falling on a given area per day, let's say, right? So if we look at the size of this little curve in winter, the total area under this is going to be very small. That's because the solar resource is very small. And the sun rises late and sets early in winter. And as we move towards summer, obviously the total amount of the solar resource increases. Not only it increases because of this, that we have at solar noon, we have less of a path through the atmosphere. We have more sunlight reaching the Earth. we have a total increase of the amount reaching the Earth. We also have that cosine theta term here dictating the cross-section incident to that sunlight coming in, increasing. And so that's driving this going up. And we also have a second fact that the time of the day, the total duration of the day increases, at least in northern latitudes. And here at around 40, let's say 41 degrees north, here in Boston. And we have, because of these two effects, a much larger area underneath that curve. And so as we go through summer, and now finally to September 13th, and back to winter, our solar resource goes back down again. So you can calculate it, you can visualize it. That's cool. And we can plot the total amount of energy per unit area per day, essentially the integral under that curve, as a function of location around the US, around the world, per month, let's say, right? So this is January. This is kilowatt hours per meter squared per day. So it's just taking the integral of the curves measured. So it's accounting for cloudy days, which kind of has a depressive effect. This is an envelope function, if you will, the maximum you could get. And then, of course, local weather patterns will suppress that, drive it down. So this is the real map of the United States. And you can see in sunnier areas that are less cloudy, over here, for example, in Arizona and New Mexico, there is a large solar resource even in January. Atlanta, which has half of the number of sunny days per year as Phoenix does, even if it's at the same latitude, is getting about half the solar resource. They got a short end of the stick. Again, this curve right here is the envelope function, right? And off of that, you can only go down. You can only decrease the amount of solar resource actually arriving at our feet here. And so this is in January, and this is all in the same color scale here as we move through the months. So we'll move from January to February to March, April, May, June, July, August, September, October, November, December. So you can see across the United States how the resource is distributed geographically. The general trend that as you go from south to north, you have a decreasing solar resource holds. You can also see the influence of local weather patterns as well for the same latitude. So that's pretty nifty. And another nifty fact, if you look at the year average value, annual, this is the annual average value. Here in Boston, we're averaging around 4.5 kilowatt hours per meter squared per day. Phoenix, Arizona can be upwards of 6, somewhere in the outskirts. It's not that bad. it's only a few tens of percent. It's not that bad. I tell myself. I don't believe it. I don't believe it myself either. But I try to convince myself of that during winter. All right, let me show you the seasonal and diurnal variations from. We're increasing the level of sophistication as we go along, right? We've assumed you've done your readings. We've started with some simple examples, and now we're really taking it one step further, which is to introduce the full 3D model. And I'm going to do that by use of this really cool app that's available here, right here. This is you standing on the Earth, and you can drag and pull this around. You can see this north, south, east, and west. So I'm going to pull it up a little bit just to give us a little bit of perspective. Still, south is facing toward us, north is away. The sun will rise in the east and set in the west. Now, if let's say I pull the date back to September. So this little tool is so cool because it recognizes your IP address and situates you at the proper latitude. So we don't have to touch that at all. It's approximately right. We're at about 41 degrees. We're right here in September. And in terms of time of day, we can pretty much just cycle through the time of day if we like. We could, for example, start animation. Let's see, this is going very fast right now. I'm going to slow it down. So you can see the time of day moving right over here. And you can see the relative to our vantage point on the surface of the Earth, this little yellow dot here and this yellow line is tracing through the path of the sun in the sky from our perspective. And so as we go through the seasons, I'm going to speed it up just a little bit so that we pay more attention to the position of this yellow line and less attention to the diurnal variations. We're paying more attention to the seasonal variations. I'm going to vary the seasons by force here. I'm going to go back to July or June, if I may. Here we go. Yeah, so there's a number of other lines right here, and they're all explained very carefully. There's the hour of ascension, which would be Prime hour circle, yeah. So I believe, I'd have to go back and double check all of this, but I believe they relate to the, what would be the sunrise and sunset of that given day. Let's see if our hypothesis is correct. No, it is not. That would have to be, since it's varying in a systematic way from January through the summer and then back to the winter, I'm imagining this has something to do with the direction of the sun relative to the Earth, right, as it traces that ellipse through the sky. So let's pay attention to that yellow line for a minute. That's the one I want to attract everybody's attention to. Now we're in June, so in the height of summer, and relative to this observer right here, the sun is further up in the sky, right, just like we traced out right there. And now as we go to winter, that line drops closer to the horizon. So a couple of things happen. If we look like this, for instance, now we're looking straight down on the observer. In wintertime, the sun will rise in the southeast, right, and it'll trace this arc through the sky and set in the southwest over here. In the summertime, the sun will rise almost in the northeast, north of east, right? Just slightly north of east. And that's why if you have a north-facing window and you put your little plant on the windowsill, it'll get a little bit of direct sunlight early in the morning and late at night. It's when the sun is tracing this part or that part through its trace in the sky. So it's worth sitting down with one of these plots, toying around with it, getting accustomed to it, and understanding really how the sun traces its arc throughout the sky relative to our position right here on the Earth. If we shift this further up north, really interesting things begin to happen. So for example, my wife is from Sweden. If we go to her hometown right here, in the middle of summertime, right at the solstice, you can see the sun traces this awesome route from north to north, barely leaving the horizon. If we look at, again, from the perspective of the little creature here, that yellow arc is really close to the horizon. Maybe it goes up about that high, but it continues going all the way to the north. And if you keep going north, it will never set during the middle of summer. It'll just be light all the time. And you can see here, it just traces that orbit right around there. It's all trig, folks. We can do it. We can sit down and we can work through the equations by hand. I did that once. It took me a long time. I didn't learn that much. I would instead advise you to go to one of these simulations right here, but to understand all the inputs into it, all the different components, right? The fact that the sun, the Earth is moving around the sun as a declination angle, seasonal variations, and so forth. Very useful tool. You have the website link right here, and yeah. So from this tool, actually, one last tiny thing. From this tool right here, we can understand why, okay, this is real stretch, and forgive me, social scientists in the room for doing this, but I have to project a little bit of science onto human behavior. How far west is Madrid from GMT? Madrid, Spain. It's 3 degrees west of the Great Meridian, right? So the line that divides the east and the west hemispheres is 3 degrees west. But it is 1 time zone earlier than London, right? So it's in the same time zone as Germany and all the other cities that are east of London. And this is just for convenience factor. If you're traveling from one continental European country to the other, it just makes sense to have everything be on the same time zone. You get to work at the same time, sort of. Pick up the phone, call somebody, you're doing business. Now, relative to everybody else in Europe, though, is the sun setting later or earlier if you're that far west in your time zone? Later, right? So the sun is setting later if you're there. So if you're eating according to the sun, not according to what your watch is saying, but if you're choosing to eat dinner when the sun is setting, when will your watch say, oh my goodness, it's really late? When you're in Berlin or when you're in Madrid? When you're in Madrid, right? So again, I'm not saying that this is the sole reason for social behavior being a little different on the Iberian Peninsula, since Portugal also eats very late and they're in the same time zone as London, but it could be a contributing factor, right? The sun is still up in the sky when it's 5 p.m. in winter, let's say, and where in Germany it's set a long time ago. So these are just little things to keep in mind. An easy way to calculate that, when is the solar noon, you look at the Earth more or less like we're looking at this right now. We have 360 degrees. We divide that into 24 time zones. And then we say, okay, about 15 degrees each, right? And then we can begin counting from there. If in Boston we're 41 degrees north, but we're 71 degrees west, right? We can say, okay, we should be, for GMT -5, we should be at around 75 degrees, and so we're a little earlier, so we do things a little earlier around here than what the solar noon should be telling us to do things. Wake up a little earlier, go to bed a little earlier, and that's why students you're like, dang, there's no nightlife around here. I'm not saying that's the only reason, but it could be a contributing factor, whereas the opposite happens when you're far west in your time zone. Okay, so again, just trying to wrap our heads around the solar resource and around the world around us so that we can answer that little child in the shopping mall when they come with questions. What are these? Solar trash compactors, right? At the student center. Anna's Taqueria is right over there. Dunkin' Donuts is there, right? So these are solar panels mounted on the tops of those. And what the solar is doing is charging a battery inside. Once the trash reaches a critical level, a sensor is triggered, it stops you from opening this bin, and it compacts the trash, right? And then releases and allows you to open and put more stuff in. And what it does is it minimizes the number of times between trash pickups. If labor is a large portion of the cost of trash management, of waste, of refuse management, then it eliminates some of the labor, transferring it instead to the technology. And so installing these at the student center, I had a little bit of a pet peeve. You have the angle of the sun right here, which we just walked through, 18 degrees in summer. And it just so happened to work out that, and these numbers were approximate. This was me going with my kind of engineering sense. That's about 45 degrees, count the number of paces, equilateral triangle, estimate the height of there. But in the middle of summertime, when you are at the solstice, there is no direct sunlight hitting this trash can because of that overhang way up there. That's not a problem for this particular trash collector, since those panels are way oversized for the amount of energy that the trash collector actually needs. And there is a fair amount of what we call diffuse sunlight, meaning sunlight being scattered off of other things. That's why this portion of the image looks white. It wouldn't look white if there was no diffuse scatter. It would look black, pitch black, if there was nothing to scatter the light off. Like in outer space, there's nothing to scatter. That's why it looks like a black night. But instead, there's a large amount of diffuse light. There is still some sunlight reaching it, and since the panels are way oversized and the system is over-engineered, it still manages to acquire enough energy to compact the trash, and it doesn't have a catastrophic stop. But it was an example of somebody not really thinking much about the direction or the angle of the sun in the sky. They probably installed it sometime around March, right when the snow started to melt, and the sun was right around here, right? And so the angle was around there, and it made it into the trash collectors. But as the summer came along, it got shaded. So it's something to keep in mind when doing a solar installation. It is important to calculate these things, and I just pick out one small example. I'd encourage you to walk through. I was going to have that be a small little in-class example, but since we're running short on time, I'll just give it to you like that. Okay, fixed versus tracking systems. So if the sun is moving as a function of season and as a function of time of day throughout the sky, and we can see that very nicely again through our demo right here. So if the sun is actually moving, one embodiment would say, okay, I know more or less what the sun is going to do as a function of season. Forget the diurnal variations, but just the seasonal variations. I know that the sun is going to be on average somewhere around here, somewhere around my latitude. So if I point my panel at latitude tilt, right? Since this angle was, 41 plus 23. This angle was 41 minus 23, so this one would be right around 41 latitude. So if I aim my solar panels at latitude tilt, then I'm going to get, on average, some pretty decent power throughout the year. I'll have a little less in winter, a little more in summer because, just because of the amount of solar resources available. But all in all, I'll be all right. At most, I'll be off by 23.5 degrees. You can do that, and that's called fixed latitude tilt. And typically, you'll face the panels south, approximately. We'll get to that in a minute. Depends on local weather patterns. If you have fog in the morning, for instance, you want to face them a little to the west. But we'll face them south and at latitude tilt. Or we can decide, no, let's actually track the sun throughout the sky throughout the day. And so we'll start in the east in the morning and have it rotating through on one-axis tracker. throughout the day. Or we can have a 2-axis tracker where it rotates to follow the sun throughout the seasons as well, a kind of a north-south tilt. And that's what's plotted right here. This is a quick approximation of the fixed 1-axis and 2-axis trackers for a given system in Boston using a simulation tool called PV-Watts. There's a link to that. It's based on the National Renewable Energy Laboratory website. There's a link to that at the end of the slides. But this shows you the total system output in terms of kilowatt hours, in terms of hours per day. I think, yeah, it's a little bit of an odd units there on the y-axis, but it shows you the relative gain that you would get by going to a 1-axis and then finally a 2-axis tracker. So in many places, it makes sense to go to a 1-axis tracker, since especially you broaden out the peak near the peak hours of the day, and that's really good. But not always does it make sense financially to go to a 2-axis tracker. You're adding another motor onto that thing. It's really not gaining you that much. Obviously, you have to calculate it out yourself for that specific location, but by and large, a generality, a 1-axis tracker makes sense for a flat panel. Now, if you have a concentrator lens in the front and it has to be looking directly at the sun, then you're kind of forced to go to a 2-axis tracker. OK, and there you have your total system output, which is just the integral under the curve over the entire year. So definitions, should have done this before, but direct sunlight, looking directly at the sun, and then diffuse sunlight, or scattered light, coming off of other things, right? So diffuse sunlight would be coming from the other angles in other directions in the sky. The direct sunlight would pretty much be at the sun, plus or minus a few degrees. And we have different ways of measuring this would be flat plate. Up there on the upper left, it says flat plate facing south, latitude tilt. Just like we said, it's facing south in the United States. That's good. Latitude tilt, meaning it's tilted at our latitude. So if we go from the southern tip of Florida and Texas up to the northern tip of Minnesota, we'll be tilting it more and more toward the south, like this, going from Texas to Minnesota, right? From Texas to Minnesota. And so latitude tilt, facing south, flat plate. This is essentially accumulating all of the sunlight, the direct and the scattered light, because it's all being collected by that flat plate there. This map, on the other hand, is for a 2-axis tracker, and it's looking at the sun plus or minus 2.5 degrees. And so it's really only picking up this right here out of the sky. And when it's sunny all the time, you're golden. You're tracking the sun. You're actually getting more energy than you would if you just had a flat plate, because the cosine theta angle is changing throughout the day if you have a flat plate. When the sun is in the morning time, you have a flat plate like this. So if my sunlight is coming in like this, and I do cosine theta of the angle, I'm only getting a very small amount of the incident sunlight projected onto this plate right here. Whereas in the middle of the day, now cosine theta is 1, I get the full sunlight. But if I have, for instance, a tracker, I would be able to face this panel due east and then track it throughout the day. And that's where I'd get this additional energy boost here in the mornings, right there, from the tracking system. So if I have a tracker, I get a big gain in the places that have a lot of direct sun. And if I'm only looking at a very small solid angle of the sky, if I'm only looking at, say, this little portion of the sun, on cloudy days, most of the sunlight is coming off of the diffuse light, not from the sun. If I have a flat plate, I win. If I have a concentrator, I lose on a cloudy day. And so that's why in some of the regions of the United States that are notoriously cloudy, I won't point to anyone in particular, it's actually better for non-concentrating solar in terms of total energy output. And in other regions of the United States where we have a lot of sunny days, you start having 2-axis trackers making sense. And it's just really the ratio of these two maps. Whoopsie. This one, which is flat plate, and that one, which is concentrator. You see over here, we win if we go for the concentrator. And over here, we get more energy out, more energy out if we use the flat plate. Now that's just energy. Obviously, costs and economics factors in what it takes to install it. Okay. And weather patterns. I promised I'd get back to this. Interesting to note that right near the equator, we have this drop of the insolation. And there are these beautiful maps put out by, again, by this NASA Earth Observatory that show you the cloud fraction coverage of particular spots around the planet. And you can see that right near the equators, typically we have these beautiful tropical forests, and those are, obviously the high cloud cover in those regions is blocking out some of the sun. And likewise, you can see that dichotomy between Phoenix and Atlanta, same latitude again, but Atlanta having a higher cloud coverage than Phoenix, and hence a lower solar resource, a lower insolation. So you see how this kind of ties together. That's all predictable, in a sense. This is unpredictable at a local level, for one system, right? If the sun is tracing its route through the sky, and you have that envelope function that you've just spent so much effort calculating out with all your trig functions and the computer simulation, the code that you've just been given here, and now a cloud comes over, some random cloud that was very hard to predict, and you just have one panel, one tiny little thing like this, and the cloud goes over it, boom, all of a sudden you get a drop in your instantaneous power output. Boom, drops again, another cloud drops again, and then a thunderstorm in the afternoon. So a meteorologist could have told you that this thunderstorm was coming, but a meteorologist would be hard-pressed to be able to predict the evolution of a tiny little cloud over your system. And so the question is, to what degree are these local weather patterns predictable and unpredictable? And hopefully, some of you over this class will be able to help answer that question by analyzing data from tens of thousands of systems that have been installed throughout California in local geographical systems, for example, in the Los Angeles region, San Francisco region, and so forth. If you start averaging the curves, the energy outputs as a function of time from a variety of systems throughout a neighborhood, you can probably average out the small tiny clouds. You probably can't average out the thunderstorm, but you probably could have predicted that the thunderstorm would have come along, right? And so this is a hot area of solar research at the systems level, is trying to understand to what degree are PV systems predictable? To what degree can the power output of a PV system or an ensemble of PV systems be predicted in advance, so we don't wind up in a situation where all of a sudden we have this catastrophic drop of a cumulative PV system output of, say, 30%. And meanwhile, it's a hot summer day, everybody's air conditioners are going, and we cause failure of the power grid, kind of worst case scenario. So this boils down to intermittency, with the short time constants tend to be less predictable, cloud cover, and it's relevant for predicting power supply reliability. And the longer time constants tend to be more predictable, the diurnal or seasonal variations, and these are relevant to calculating total energy output annually. And oftentimes when we just work off of these long time constant variability issues, we're assuming we have access to easy storage. Right now, the solar panels on top of my roof, they're producing in excess of what we're consuming right now, because neither my wife or I are at home, and they're injecting that power into the grid, and the grid is serving as our big battery, as our storage unit. And I'm riding free. I'm a free rider right now. I don't pay for that service necessarily. I do to NSTAR. But they're not charging me extra for the service of using the grid as my big battery. Another thing to keep in mind is that we're calculating all of this on the basis of engineering and scientific principles. We're calculating the solar resource, which is a good, important first step. Now, if we look at the actual solar installations by year and by country, this is a big table, but follow me on the two underlined red lines here. DEU, that stands for Deutschland, Germany, and USA. We'll see that Germany has about 7 times more solar installed cumulatively than the United States does. And yet, if we look at the solar resource in Germany relative to the US, this is average annual, same scale, going from 900 to 1,200 kilowatt hours per kilowatt per year. We can see that there's a lot more sun in the United States than there is in Germany. So there's something else going on than just the solar resource. And that's the economics. That's why we talk about the policy and economics later on in class. That's why we dedicate a sizable portion later on talking about that. Lastly, our final learning objective before we halt for questions and for comments, we need to estimate the land area needed to provide sufficient solar resource for a project. And this is really where your homework picks up, and we'll spend some time in recitation walking through this. But it's important to get your units right. And so I want to do a quick quiz right now. Think in your minds which of these properties correspond to which units, or are described by which units over here on the right. So do kind of a linkage in your mind, one-to-one, connect, 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 without looking at your slides. And then we'll do it in 3, 2, 1. Those are your answers, right? So the ones that usually get confused are power and energy, kilowatts and kilowatt hours. The not saying this is easy, but the way to remember it, the easiest way to remember it, would be to remember that the power-time product is equal to energy. So if you have power, instantaneous energy burn rate versus time, some plot that looks like this. If you take the integral of that curve, that's your total energy. So in terms of units, current, voltage, power, and energy, a hairdryer versus a fridge, which is more likely to blow a fuse and which is more likely to blow your budget? Hairdryer is more likely to blow a fuse. Why is that? Yeah, high voltage, well, high current, really, because everything's running 120. It's a higher current. It's pushing the wattage up to around 1.517, so 1,500, 1,700 watts. So it's running close to the 15 amp limit. And the fridge, on the other hand, is probably an order of magnitude lower. But the fridge is running all the time, and your hairdryer is only running a few minutes a day. Right? So in terms of blowing a fuse, it uses a large amount of power for a very short amount of time, whereas the fridge uses a smaller amount of power for a longer amount of time. And the integral under that curve winds up being more, typically, than your hairdryer. That's the total amount of energy. And you pay by the energy. You pay by the kilowatt hour to your utility company, and that's why it would blow your budget. Yep, oopsie. So the numbers work out to somewhere around 1 kilowatt hour per day for the fridge and about half a kilowatt hour a day for the hairdryer. A kilowatt hour is how much in here? 18 cents? Most people pay about 18 cents per kilowatt hour. And so you can calculate how much it costs to keep things running in your house. Most of us don't usually think about that. And last point. In your homework assignments, you're going to be asked to size out systems, PV systems, photovoltaic systems, in different parts of the world. And the easiest way to do that is if we take a panel and we say that this panel right here is rated at a certain amount of power, right? So under peak illumination conditions, when the panel is seated at incident sunlight, so the cosine theta term is 1, and the incident solar resource is 1,000 watts per square meter, so around AM 1.5 conditions, this panel right here would be producing, this one's tiny, it would be producing around 6 watts peak. But most of these panels over here are producing somewhere around a few hundred watts peak. And so the panels are rated in terms of watt peak because the panel manufacturer doesn't know where you're going to install them. You could decide that you're going to install it in Alaska, in which case it's going to produce about half the energy that if you installed it down south in the continental US in, say, Arizona, maybe a third of the energy. And so it doesn't want to rate the panel in terms of the energy output. It's not going to guarantee that you're going to get a certain energy output off of the panel, but it'll guarantee that the panel was rated at a maximum power of such and such under standard testing conditions. Now that's good because you can generalize it, which you'll do for your homework, but it also has a downside because standard testing conditions aren't real world conditions. The panel isn't always operating at 25 degrees Celsius. The panel isn't operating always at incident sunlight normal, right? And so the gap between actually knowing how much the panel is going to output in terms of its energy for a specific location and what our calculations, the back of the envelope calculations will give us, that gap is, from an economics point of view, there's a lot of money to be made there. If you understand really well how much a given panel will output, you can then predict to a much finer degree what you should be charging your customer for installing panels in a particular location. Right? So there's a lot of work being done right now, more on the business side of pulling the systems engineers along and trying to increase the accuracy of predictions. And so with that, I will leave off on this slide. We can get to it during recitation tomorrow at 4. I welcome your questions here at the front if you have any. Otherwise, I'll see you tomorrow.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Today we're going to talk, or it's the first technical discussion of the actual solar cell device itself. We talked last class about the sun and about the nature of the solar resource. Today we're going to be talking about the interaction of light with matter. In particular, we're focusing on light absorption. This lecture could alternatively be called light not getting absorbed or optical losses. Both are important and both are related, as we'll see. So this is part of the fundamentals of the course. Just to situate ourselves, we're here right now in the fundamentals, the first third of the course. Then we'll talk about the technologies and the cross-cutting themes. And what we're going to talk about is extremely important because it allows us to understand the technologies once we begin discussing them and we discuss cost trade-offs of implementing this particular technique to the wafer to absorb more light. We can appreciate how much, we can quantify the impact of that technology development, and we can also later on ascribe a cost to it to determine the total cost-benefit analysis. So, convergent efficiency is really what dictates the performance of the device, the solar cell device. It's how the solar cell device converts sunlight, the input energy, to some usable output energy, which is in the form of electricity, typically from a solar panel. So, the electricity coming out of these leads, for instance, right here. And that conversion efficiency, that simple equation, for most solar cells can break down into the following. You have inputs. Sorry for the small font here. This reads solar spectrum. That's your input. Your output, which is the charge collection. It's a collected charge coming out of your device. And a bunch of steps in between. So from the solar spectrum, we have to absorb that light. Then we have to excite charge within the material. Then that charge has to move around inside of the material to get to the metallic contacts on the front side. Charge separation has to occur for there to be a voltage. And finally, the charge collection process. And so the total efficiency of this device is the product of each of these individual processes. Right? And so if you're making a solar cell device, and I know about a third of you are, based on your background surveys, this diagram right here will ring true to you. It's Liebig's law of the minimum. What this is representing is a barrel that has water being dripped into it, and the water will flow out of whatever piece of wood is the shortest. And in the case of a solar cell device, you can ascribe a certain name to each of these pieces of wood. We'll learn what each of those are with time. But one of the big ones is optical losses. And the optical losses tend to be rather severe on some of our lab scale cells. And so one of the easiest ways of boosting efficiency is simply to take care of your optical losses and to minimize the amount of light reflected or not absorbed, and to maximize the amount of light that's actually absorbed. And so to do that, there are a number of standard techniques and some cutting-edge research areas. And I'll attempt to give you a broad overview and survey of both, assuming, of course, that you've done your background reading. So the learning objectives. The first is to be able to calculate the reflectance and non-absorption optical losses of a solar cell. So this is essentially all the light that's not absorbed. Right? We want to be able to calculate that. The second is to describe the physical underpinnings and the implementations of 4 to 5, there are 5 here, I added 1 at the end, 4 to 5 advanced methods of reducing optical losses. So there are technologies, techniques that we've used, that we've developed over time, that we can use to minimize the optical losses, to minimize the amount of light reflected or not absorbed inside of the solar cell device. So to think of this pictorially, we can come up with the following diagram where we have some incident energy, in this case incident light. Here's our medium. Here's the amount of light that gets absorbed. Here's the amount of light that gets transmitted right through, that does not get absorbed within the material upon passing through it. And there's a certain amount of light that just gets reflected off the front of your solar cell device. We want to obviously maximize this part right here. So to begin, we give a quick review of light, the nature of light. This is going back to the particle-wave duality of light. It will be useful alternatively to think about light as a particle, quanta of light, or to think about light as a wave, depending on what light management technique we're going to be describing. And in particular, I'd like to just highlight these equations over here, the notion that one can define the energy of a photon coming in, and that photon has a certain wavelength, a certain frequency, a certain wavelength associated with it, frequency and wavelength, related, of course, by the speed of light, Planck's constant, and so forth. So just to situate ourselves with broad numbers. When we dive in and talk about spatial dimensions in relation to the wavelength of the light, we're in a situation where we can actually have a horse sense, common sense about it. The visible photon wavelengths are usually in the hundreds of nanometers. Right? And the solar spectrum peaks somewhere around 550. Just good numbers to have in mind. So this was that solar spectrum, the integrated solar radiance versus wavelength, right? And the second point that is equally valid, we can describe the wavelengths of the incoming light, lambda, or we can describe the energies of the incoming light, this E sub pH, the energy of the photons. Right? And so just to situate ourselves again, the visible photon energies are typically in the range of 0.6 to 6 eV, electron volts. Again, with the peak of the solar spectrum at 550 nanometers, somewhere around 2.3 eV. Good. So a simple thing to keep in mind for those high-energy particle physicists in the room, that when we're talking about visible light, we're interacting with a very specific type of electron inside of our system. It's the valence electrons. These are the electrons that are typically most loosely bound inside of a system, or I would say in the outer shells of the atoms within the material. You're typically not interacting with core shell electrons with visible light. For that, you need X-rays. So this is just something to keep in mind when we start looking at the wavelength dependence of absorption inside of a material. You can have, for example, in the visible range, a decreasing depth of penetration of the light with increasing energy, whereas with X-rays, it's the exact opposite. It's because you're dealing with different types of electrons in the material. So just to situate ourselves, I know we have a fair number of physicists and chemists in the room. That's a message geared toward them. Let's describe how light interacts with matter. And first off, come up with a few variables, define a few units that will make it easier for us to understand how light is interacting with matter. And so here, what I've done for you is placed the equation that describes the complex index of refraction of a material. What this means, effectively, you can think about this refractive index of the material as being comprised of two different components. For now, it's going to be fairly cerebral, but I'm going to reduce it to practice in a couple of slides. The real component of the refractive index, and the refractive index is material-specific property. So if I have, for example, silicon, or if I have silicon nitride, or if I have a particular type of glass, it'll have a particular refractive index. It's comprised of a real component, which indicates the phase velocity inside of the material, and an imaginary component, which can be thought of as an extinction coefficient. And it is related to the attenuation of the light intensity as it travels through that material. The measurements, for those who have already taken measurements before on a spectroscopic ellipsometer, this is how you measure that parameter up there. We don't have to dive too deeply into that for the purposes of the class. It's just for background. Why these values are important. These values here describe the interaction of light inside of a medium, inside of a material. And we use that information to calculate engineering relevant parameters such as reflectance of light off of a surface. So if we want to calculate what is the reflectance of light off of this silicon right here, I can calculate it by knowing these properties right here, by knowing the real and imaginary components of the refractive index of silicon in this case. And the reason that's important is because we want to minimize reflection off of surfaces, right? So I've come up with the first equation right here, which is describing the reflectance from air to a solid, in this case, from air, where the refractive index is 1, to a solid, namely, say, for example, silicon, right here, or glass, which has a finite refractive index, typically greater than 1. And so I have an equation here that describes the reflectance. Let me dive a little deeper into it and try to understand what exactly that equation is telling me, right? So from the folks who have studied mechanics, many of you are mechanical engineers in the room, you may recall studying a problem wherein you have two springs that are connected. They have different spring constants, different stiffnesses, shall we say, and you excite a wave over here, it travels down, and when it reaches the interface between the two, part of the wave is reflected back and part continues through. The speed of the wave is changing as it goes from one spring to the other, because the stiffness is changing of the springs. And the amount reflected can be described by this equation right here, which looks awfully like the equation right above it, which is describing the amount of light reflected off of an interface. And in reality, those n's have a very similar meaning, the n and the z. The n in the case of light, which is the real component of the refractive index, might I mind you, this parameter right here, this indicates phase velocity in a material. It could also be thought of, very loosely, as the ability of an electromagnetic wave coming into a material to slosh those electrons around. Not exactly a stiffness coefficient, but it bears some rough resemblance. So this is a method for you to gain a foothold in this new area of understanding the refractive index of a material based on something you've already seen before. Okay. So I would advise taking this analogy as far as it will go until it breaks down. Push it as far as it goes until it breaks down, and you'll see at some point it actually does, but it's a useful place to start. So I'm going to ask you a couple of questions. This might be rather new for a lot of folks, but the purpose of asking these questions is to get you thinking, and eventually we'll get to a point of heightened understanding as a result. Tinted windows. So if you have a tinted window, what is typically happening at that tinted window? Why can't you see inside? What do you imagine is going on? So let me go back to this reflectance equation right here, this one. Right? How would you modify a reflectance off of a window, let's say? And let's drop the k's for now. Let's leave those aside and just focus on this parameter right here, n minus 1 quantity squared and plus 1 quantity squared. What would increase the reflectance off of that window if I have a larger n or a smaller n? If I have a bigger n, right, I would get bigger reflectance. Is that right? Right. R goes up? Well, you'd have to plot it out, I guess. Right? So if I change the refractive index of the material that I'm working with, I can change the reflectivity off of that interface, off of that surface. So if I add a coating, for instance, to a window that increases the reflectivity, then the amount of light that is able to escape from the inside to my eyes decreases. Now, with normal incident light, there is a beautiful symmetry involved. That is, the amount reflected off of one side is equal to the amount of light reflected off the other side. Right? So just the same way that I'm losing the ability to see inside, the folks inside are also losing the ability to see out. But they can still see out. Why is that? Why is it that with the same reflectivity, they're able to see outside and I'm not able to see in through that tinted window, through that car, for example, that's driving by with the tinted glass? Why can't I see inside, but they can see out? What's going on? Yeah? I hear somebody.
The light on the outside is much stronger in terms of the absolute amount of light being reflected.
Yep, exactly. So yes, the reflectivity as a percentage is the same for both parties, right? But the amount of light, the magnitude of the light from the outside is much, much greater than it is on the inside. Can anybody give me just a gut sense? If I'm outside on a sunny day, how much brighter is it outside versus inside right here? Factor of?
100.
Maybe a factor of 10, somewhere in that range. And so when you walk outside on a sunny day, you'll notice your eyes adjusting a little bit. It'll take a minute. And when you walk back inside, it'll take a minute for your eyes to adjust as well. That's because of the difference in intensities. So if you imagine being outside of that car and having 10 times the amount of light being reflected, right? That small amount of light that is actually transmitting through the window from the car to the outside world will be washed out by the amount of reflected light. Whereas if you're inside the car, there's a lot of light coming through that window. Even though a lot of it gets reflected, there's still a sizable amount coming through. And the amount of light that gets reflected off that window of the internal light is small in relation to the outside light that is being transmitted through that window. So it's important to think about these processes, both in terms of the reflectance as a percentage, but also the magnitudes of the light involved. What if that glass pane was flipped around? Would it change anything? If I took that glass and just flipped it, would it change it? What about the symmetry argument? Right? That the amount of light is reflected, the R, reflectance, is the same from both sides.
Is it not the case that there's a coating on the outside? So is
Yeah.
the change in refractive index is that it's an abrupt change from the outside looking at this coating. Because on the inside you're going through some medium of glass which is more index matched than the outside.
Yeah, so I would advise you to actually walk through that calculation. And what you'll find is it winds up being the same. And it's because you have to take all reflectances off of all these interfaces into account. There are, in fact, 3 interfaces. The air, the glass, the anti-reflection coating, and the anti-reflection coating the outside. This, of course, without getting into quarter wave effects, which we'll get into a minute, there are some higher order effects that deal with phase change, which we haven't discussed right now. We're just assuming that all of these layers are well above the wavelength of the light in terms of thickness, and that these equations, these linear equations, are valid. Very good. So this is just to get us situated with this new concept of reflectance. And again, a very powerful equation. Keep in mind that this is a very specific form of the reflectance from an air into a solid. If you're going from a solid into a solid, you'll add your N1 and your N2, depending on what material you're going from or what material you're going into and what material you're coming from. Right? So we're happy to walk through that perhaps during recitation. Okay, so what we're going to do now is we've talked about reflectance off of surfaces. What I'd like to do is talk about a light absorption inside of a material. So let's imagine that through the techniques that we're going to be discussing later on in lecture, we managed to minimize the amount of reflectance off the front surface. And now the light that's incident on the material is actually going to go inside and get absorbed by the material inside. We need to be able to understand how light gets absorbed inside of matter. And for that, we apply a very simple formulation inside of this class, which is called Beer-Lambert's law, which is a very powerful, very simple yet very powerful formulation that describes not only the interaction of light with the solar cell material, but also light through the atmosphere, light through water, many other forms of optical absorption. And for that, I'd like to call Joe up for a quick demo that he put together that will allow us to actually plot out Beer-Lambert's law. And I'd like to start with what I would think of as a simple hypothesis. What we're going to be doing, and Joe will explain this in a minute, what we're going to be doing is taking many sheets of material. This is just some polyethylene material, a little bit discolored. And we're going to shine a laser down onto this photodiode. The photodiode current will be measured by this little current meter right here. And we'll be inserting these panes of plastic in the middle. And as we increase the thickness of the plastic, applying good pressure in between to minimize the reflectance, the air gap, for instance, as we increase the thickness of the polyethylene, we will plot the total transmitted light as measured by that photodiode. And so I'm going to come up with a hypothesis of what's going to happen. I'm going to say that if we double the thickness of the polyethylene, that we're going to have the amount of light going through. And if we triple, we're going to reduce it by a third. And if we quadruple, we're going to reduce it by a fourth. And let's see if that hypothesis is correct. It's not, but we're going to test it. And it's a logical thing you might assume. And then we'll walk through a derivation that will correct our missed logic. So go ahead, Joe. Take it away.
So if you guys want to play along, that's fine too. I know there's lines on the side of your notes. You can make a little graph paper, and it comes out looking really nice. So basically what we have is a laser pointer and a photodiode. And the current out of this photodiode is directly proportional to the light hitting that photodiode. And it has a quantum efficiency, which we're going to learn what that is in a few lectures, of about 60%. So of the photons hitting it, you'll get a certain number of electrons out, and that ratio is 60%. And so first of all, we're going to see what it's like with the power of our, So right now we're getting about 1.32 milliamps. So Tonia's going to plot that. And then as we keep increasing and put one layer of polyethylene, that drops to 0.75.
So before we go on to the next one, what do people predict the next dot is going to drop the total intensity to? Is it going to be kind of a linear line like that? You would expect it, right? Because you're doubling it. So you'd expect the intensity to drop by another factor of 2. Why not? Where am I getting a mistake here? Somebody says exponential. There's kind of the sense that it should be exponential. Why don't we add some more filter in front, and we'll see what exactly this comes out to be.
This is with 2.
2?
Now we get 0.43.
0.43. Okay. All right. Why don't we do one more just to see what sort of trend we're getting? Still a bit of a toss-up. 0.26. Ah. Wow. Okay. So it didn't go in a straight line. It's actually starting to curve down. Cool. Okay.
And we keep going. 0.16.
1.6.
0.10.
0.10. Okay. Look at that. What sort of curve is it? Exponential. It looks like one at least. And we can test whether or not that hypothesis is correct by an exponential fit, which happens to match pretty well. So
now, one other quick thing you notice is that if you look at the fit, the first point's a little bit higher than that fit. Anyone have an idea of why that might be the case? What are we ignoring in this experiment?
The reflections from each bit.
The reflections, yeah. So the first one, you reflect light, and a certain amount gets transmitted through that front surface and then absorbed. And so right now we're ignoring this 1 minus r component. But it's so small that it really doesn't matter for this experiment. These things don't reflect a lot of light. So, good job.
cool. Well, why don't we give a quick round of Joe? Well done. Can I grab one of those?
Absolutely.
This is going to be important for the Limburtian scattering demo.
Oh, sure.
Yeah. Cool. Okay, so we notice that we have some exponential character to the decay of the intensity of the transmitted light through a medium. And the amount that's absorbed is following another trend, which is just 1 minus that, right? So it's the amount of light that's absorbed is following a curve that looks something like that, right? Okay, so let's look through the formalism of Beer-Lambert's law and try to understand why it is that we come up with that exponential function right here. So if we assume that light is coming into a medium, and light is decaying in some function through that medium, and a certain amount of light is transmitted, we know, of course, from our little experiment that it follows some exponential function, but how do we justify that to ourselves? Well, first off, we're going to ignore reflections off the front surface. Right? We just talked about them. We can calculate them. Let's leave that aside for now as a parallel calculation. We're just concerning ourselves with what's happening inside of the medium. So if we assume that the change of intensity within that medium in each little delta thickness is going to be affected by some sort of scattering intensity within the medium. And this sigma here can refer to a variety of processes. It can refer to absorption events that result in the generation of free charge. They can refer to absorption events that just heat the material up and generate phonons, so lattice vibrations. There are a number of processes embedded in this sigma, and that's why this formalism is so powerful, because it doesn't care really what the physical nature of that sigma is. It just matters that there is an absorption per unit distance, thickness traveled inside of the material that is constant throughout the entire material. So the sigma here is independent of thickness throughout. And then as you integrate through, you wind up with that beautiful exponential function at the end. The sigma L times n, we collapse the n and the sigma here into an alpha. That alpha is an absorption coefficient. The L is the total length or the total thickness of this medium right here. So if we increase the total thickness, we're going to decrease the total amount of light coming through via that exponential function. The alpha, on the other hand, is not a geometric parameter. It's an intrinsic material parameter. To put that in terms of mechanical engineering, for many of the mechanical engineers in the room, you recall from solid mechanics 2001 that you have geometric parameters that determine, say, for example, structural response, and intrinsic material parameters like Young's modulus that determine the structural response of a system. And likewise in here, in the optical, shall we say, response, we have a fundamental intrinsic material parameter, our alpha, the absorption coefficient, and a geometric parameter, our L, which is the thickness. Okay, and the beauty of this formalism right here is that we can measure experimentally, just like we did right there, our alphas for materials. And so from an engineering point of view, we don't really, to first order, it doesn't really matter what sort of scattering or absorption process is happening inside of the material for us to calculate the amount of transmitted light. We just need to know the alpha. We need to know the optical absorption coefficient. This alpha will vary as a function of wavelength inside of a material, because obviously the physical absorption mechanisms are varying as a function of wavelength. The resonances with different electronic states within the material, that light depends on the energy of the light, depends on the frequency, so there's a wavelength dependence. Yeah, and that general equation is the same one that drives the reduction of light intensity as it travels through the atmosphere. So if we increase the atmospheric path length, we'll be reducing the amount of light that actually reaches the surface of the Earth. That's why at air mass 2 or air mass 3, there's less solar flux coming down than at air mass 1 or air mass 0. The alpha obviously is going to be very different for our atmosphere than it was for these little polyethylene sheets, right? Because the nature of the scattering and absorption processes are very different for the atmosphere than it is for here, the density of the material and so forth. Any questions? Yes?
What was N?
So the N, there's a certain scattering intensity, and then there's a certain number density, for example, of the material. So this alpha here is, I would say, density neutral. What we've done is we have the alpha encapsulating the physical parameters of the material and the absorption processes all in one variable, very nicely and succinctly. And the only geometric parameter that is of essence is really our L.
It's called an absorption coefficient, but is it more of an extinction coefficient? Really, is it kind of confusing that it includes scattering clears?
So the extinction coefficient, absorption coefficient, yes, they're in solar research, when we talk about an absorption coefficient inside of a material, oftentimes we're operating in a wavelength regime of light wherein free charge is excited. But we can also keep increasing the wavelength of the light, say out to 10 microns, very long wavelength light, very low energy light. And that can excite free carriers within the material, carriers that are already excited, essentially excited them further without generating any new free carriers inside of a material. So we won't necessarily be generating more current by shining light on it, but we'll be absorbing light nevertheless in our material. So it's important to keep, I would say, the underlying physical processes that are occurring distinct. Later on, we'll get to that. For now, it's important just to, I would say, recognize that we have an exponential decay of the intensity of the light as it goes through the medium. And then over the next few classes, we're going to get to exactly what physical processes are going on. But I'm glad people are asking those questions. OK, so again, alpha is a function of the wavelength of light and the property of the medium. And let me just flash up some curves of alpha versus wavelength so people have some exposure to those numbers. Again, we're talking about an energy range quite broad here, from about 6.2 eV to 0.62 eV. The visible wavelength range would be somewhere in this regime right here, right? So a very limited band. And the infrared out here, ultraviolet over here. And we can see for a variety of different types of materials what the absorption coefficient is, right? So here we have germanium. The red would be crystalline silicon, gallium arsenide, indium phosphide, and amorphous silicon. So let's do a little quick calculation just to get us a little limber. We're starting to get into the semester, so the energy level starts going down. What we're going to do is we're going to pick a value, say 550 nanometers. Why did I pick 550 again? It's near the peak of the solar spectrum, right? It matters. And we're going to look at two different materials. We're going to look at silicon, and we're going to look at gallium arsenide. And we're going to calculate the thickness necessary to absorb 90% of the incoming light at 550 nanometers. What I want you to do is turn to your neighbor, and once again, with your neighbor, calculate what thickness of material, what thickness of gallium arsenide, the yellow curve, and what thickness of silicon, the red curve, is necessary to absorb 90% of the incoming light at 550 nanometers. You should go for it. I'll give you, say, a couple minutes. To make sure people are setting this up right, I divided by I naught, right? To absorb 90% of the light, that would be 0.1, right? 1 minus 0.9. Okay, so as you're finalizing your calculations, I just wanted to make sure people set this up right. Again, if we're absorbing 90% of the light, it means only 10% of the light is going out the other side. That means our I is going to be 1/10 of I naught, or I divided by I naught is 0.1. Right? Then we would take the log of both sides, typically, right, and solve for our L based on the alphas that we have here. Again, units of alpha would be in inverse centimeters, and so the L's that you obtained, let's go for gallium arsenide first. Did anybody manage to walk all the way through that calculation?
20 nanometers, 20 micrometers.
20 micrometers for our gallium arsenide or for our silicon?
Gallium arsenide.
Gallium arsenide. Did anybody get any other numbers for gallium arsenide? 0.4 microns? Yeah? That's sounding more in the ballpark. Anybody else? 23 as well. So I'm getting, I would have guessed that the number would be rather small for gallium arsenide. So something in the range of say, a micron in that order. Why don't we give folks enough time to walk through? I know I rushed you on the calculations here. We have material to get through, and I wanted to see it perform under pressure. But how about the silicon? Is it larger or smaller? Let's just go for order of magnitude first, and general trend, and then try to pick up the precise number. For silicon, crystalline silicon that is, with an optical absorption coefficient in order of magnitude less than gallium arsenide, is the thickness needed to absorb the same amount of light going to be greater or smaller? Greater. By an order of magnitude. Brilliant. Okay, so whatever number you got for your gallium arsenide, you could translate it fairly easily. All right, so that was at 550. And there's a lot of solar radiation right around 550. So the numbers that I have on the top of my head work somewhere out to be on the order of a micron, a little less for gallium arsenide, somewhere on the order of 10 microns or so for silicon out here. But now if we go out to 800, there's still a lot of solar flux out there. If you recall the solar spectrum, as the folks have been doing their homework, there is still a lot of flux out around 800. As a matter of fact, it continues going all the way out to here, although decaying intensity, a la black body, a la, right? And at 800 nanometers wavelength light, the optical absorption coefficient is dropped by about an order of magnitude relative to the peak of the solar spectrum. And that's why most of the solar cells that you see of crystalline silicon are on the order of 100 microns. They're typically a little thicker for some technological reasons, which we'll get to, make it difficult to handle very, very thin stuff. But if you just assume one pass through the material, you'd need about that thickness to absorb a lot of the light. And I'll pass around some of these materials right here, just so you can get a sense of how thick they are. Here we go. Actually, here's what I'm going to do. I'm going to take out the big pieces and leave the small ones in here that are already broken. And you can actually pick them up if you like. Just be aware that these little pieces of silicon are silicon's brittle materials, like glass, right? So if you have a little shard of silicon, it can poke you just like a shard of glass can. So treat it with the same amount of respect that you would a very, very thin piece of glass. But you can see here that if you look at the thickness of these materials inside of that little bin, these are small shards of silicon solar cell wafers. Their thickness is in the order of 100 microns. Those are particularly thin. You have other solar cells that are 170 microns is typical thickness for silicon. And for gallium arsenide, you can deposit thin films that are on the order of a micron thick, or less, or less. You can go down to a few hundreds of nanometers and still make, actually the record efficiency gallium arsenide solar cell is a few hundred nanometers thick. And our calculations right here assumed one pass through the material, right? That's all we gave the light. We only gave it one chance to go through the material and get absorbed. What could you envision would increase the total amount of light absorbed? What could you do to your solar cell device to increase the total amount of light absorbed inside of it? You can put an anti-reflective coating on. Let's do something much more simple.
A reflective coating on the back.
A reflective coating in the back, absolutely. Yeah, so if the light goes through the solar cell and doesn't get absorbed, that 10% of light that didn't make it, that's going to get reflected back. It's going to get another chance to go through. So if you absorb 90% of the light on the first pass, you'll absorb 99% of the light on two bounces, right? Or on one bounce, rather. On two trips, two optical path lengths through the material. And so the term optical path length is a very important term here, because the optical path length does not have to be the thickness of the material. Ideally, the optical path length through the material is much, much thicker than the actual material itself. And over the next few slides, we're going to learn how we engineer that. So methods to improve optical absorption. Generally, these are called light trapping. Not all of these entail trapping the light. Actually, most of them do. We also call them light management as a more general term. That includes reflection and absorption inside of the material. So the very simplest thing we can do on the front surface, so what we're going to do is take this step by step as light goes into the solar cell from the front side. We're going to take step by step, what can we do to improve the amount of light that is absorbed? The first thing that we can do is texturize our front surface. If we don't have texture on our front surface, if it's absolutely flat, what we call specular surface, specular coming from the root mirror, right? In Latin languages, for example, Italian specchio is mirror. So a flat silicon substrate, a specular surface would reflect some finite amount of light. And we can calculate that now because we know that it relates to the real component of the refractive index of the material. Now if we texturize our surface, this is representing kind of a pyramid type texturization. If the light comes in and some fraction doesn't go into the material, there's some component of that ray that's going into the material over here, but we're ignoring it in this drawing. We're just focusing on the lights, the rays that get reflected. That beam that gets reflected off, instead of just going back out toward the sun, it's now going toward the material again. So it has a second chance of getting absorbed. And so you just went, for example, if you have let's say if you have a 10% reflectivity on the surface, you went from a 10% reflectivity over here to a 1% reflectivity over here, right? Because now you have the total amount of light that gets reflected is 1 minus 0.9 squared, as opposed to 1 minus 0.9 to the 1. In this case right here, the amount of light that gets reflected, assuming it's 10% reflective, would be 1 minus 0.9, right? So 10% of light. And over here, the amount of light that gets reflected would be 1 minus 0.9 quantity squared. So 1% instead of 10. So texturization increases the probability that light will enter the device. And what it also does, this is a secondary benefit, is it increases the path length, the effective path length of the incoming light. And the way to understand that particular phenomenon is called Snell's law. Well, even in the absence of Snell's law, no, let's go there. Let's go there. So we have a texturized front surface. What's happening? Well, as the material goes from one medium to another, the refractive index changes. We discussed this right at the beginning of lecture. So the way in which the electromagnetic wave oscillates the electrons inside of the system is changing from one medium to another. Let's say from air into the solar cell device, from air into our silicon, for example, right here. Now, we can ascribe the refractive indices to air and to our silicon, like so, and the light path will obey what is called Snell's law, which is the product of the refractive index and sine of that angle, the angle relative to the surface normal. So a simple way to think about this is when light goes from a low index of refraction medium to a high index of refraction medium, light bends toward or away from the normal. So if I'm going from air into silicon, light would bend toward the normal, right? So here, my theta 1 is going to be greater than theta 2. My light has bent toward the normal. If this is my silicon and this white stuff over here is my air. Right? So light came in, it encountered the surface. The theta 1 was defined as the angle of the light relative to the surface normal. That was my theta 1. My theta 2 is going to be given as the ratio of the refractive indices. And because the refractive index of silicon is going to be greater than that of air, light would bend toward the normal. And so what I have on a macroscopic view over here, if this is my surface texture, light was coming in, it's now bent. And so the effective optical path length is now larger than the thickness of my device. It's kind of cool. So there are two benefits to texturizing your front surface. One is you have an additional pass, right? Additional bounce, an additional encounter with the material. So that reflected light gets another chance to go in. And the second benefit is that you're able to increase the optical path length by the delta in refractive indices and the fact that the path of the light obeys Snell's law. Now, another really interesting aside of Snell's law is that if light is trying to go from a high index medium to a low index medium, and if it's coming in at a very oblique angle like this, if you run through Snell's law, you don't get an angle coming out. It actually follows along the surface, or actually bounces back in most often, depending on the angle. And you have what is called total internal reflection, which is this case right over here. That little bounce, that friendly bounce of the light that went in, bounced off the backside, and then was reflected back in, that's a total internal reflection event. And that happens in solar modules. Right here, when light comes in, bounces off of the white backskin right here, and then gets scattered off at an angle, it can have a total internal reflection off of the front surface glass and have a second chance of getting back into the solar cells inside. So that's one of the reasons why you see this white spacing, the white colored material in between the cells, so that the light gets reflected off of there. It doesn't make it very aesthetically pleasing. You might want it to look all black. And if you do want it to look all black, what would you do instead? Instead of changing the backskin, what other component might you change? The front, right? You might change the nature of the anti-reflection coating on the glass. We'll get to anti-reflection coatings in a minute. So even if a panel looks black, there are some really aesthetically pleasing solar panels out there that look completely black. They may still have white backskin, but the glass is just very good at absorbing that light and preventing it from escaping. Okay, so to engineer front and back surface reflectances, you really have to carefully select your refractive indices and your materials that you put on either side. And it's very important, extremely important. To make a long story short, the record efficiency solar cell that was announced this past year in gallium arsenide was achieved because of good light management. And we'll explain how that came about perhaps towards lectures, maybe lectures 8 or 9. So I'm going to play a little game with you, which is to look at a swimming pool. This is a pool filled with water, which is refractive index 1.3. Air is 1. And so that's the normal view, what we have. Light bends toward the normal, right? And so you're able to look down inside the pool at stuff that is not in your line of sight, not in your direct line of sight. That's because when you look down, the ray of light is traveling like this, and then it bends toward the normal. And likewise, symmetric. So you're seeing material down there. What change of property would give you these two images over here? Let me give you a hint. In one of those two images, the refractive index of the medium inside of the pool is not 1.3, it's 0.9. It's 0.9. And in another one of these two, the refractive index of the medium is actually going to be negative. We'll call it a negative refractive index material, a negative index material. So which of these two do you think is which? Why don't you turn to your neighbor quickly and chat about it without peeking at your lecture notes. So let's see what they have here. Yeah. So let me walk through, as you begin honing in on your answers here, think about what would happen to the reflectivity of that front surface of the water, and what would happen to the angle that the light travels as it or the angle of refraction, of bending, shall you say, as the light goes from one medium to another. So if we go to a refractive index material of minus 1.3, will we change the reflectivity at all? It depends, but the answers here are shown for this particular system. It would require sitting down and walking through the equations, but in essence right here, with the pool filled with the negative refractive index material, you're really affecting the angle at which light is coming out of the pool. Here you can see the corner of the pool, which you shouldn't even be able to see. It's just that the light traveled this way and then came back because it was a negative refractive index material. Light actually did something like this. Zoop, zoop. Oh, that's just a corner. So what is in that pool? That is a computer-generated graphic. This is not a real pool. There exist negative refractive index materials, but they, not in that volume yet. These are relatively small things, and very much a study in fundamental science. So in this case right here, we have less of an acute bending of our angle of light, so we don't get to see quite as many features right here toward the edge. And the reflectivity has changed as a result of having drastically modified our reflection condition. In that particular case, I think what they were getting at is, this is coming off of an SPI website, I think what they were getting at is mostly just a change in the reflectivity, right? So they were trying to emphasize that you were modifying the reflection off the surface in addition to the angle at which the light was exiting the material. I'm going to come back to Snell's law in a minute, but for the time being, I want to move on to the next concept here, which is Lambertian reflector. You'll hear this topic or this word thrown around quite a lot in the solar cell community, and it's used rather liberally to mean a lot of things, although in optics it has a very specific meaning. So I'm going to show you that very specific meaning and then describe for you what it has very loosely come to mean in the solar industry. So a diffuse Lambertian reflector will follow a reflectance that follows a cosine theta dependence, right? So if you have light coming into a sample, the surface normal and the outgoing light ray form an angle, theta. And if the two are perfectly aligned, you get a lot of reflectance off of that angle. If the two are perpendicular to one another, you would get zero reflectance in that angle. And so the reflectance parallel to the surface here is zero. And everywhere in between, the magnitude of reflectance is varying as cosine theta. And that's the, I would say, the pedantic definition of a Lambertian reflector. Often in the solar industry, you'll hear people, probably because of a lack of optics background, just call any randomly reflecting surface a Lambertian scatterer. It's a very loosely used term. And it is wrong by the book, but nevertheless, it's one of these things that live on in our industry. So the difference between a specular reflector, the ones that we've just been analyzing right now, and a Lambertian reflector is that typically the way these are made is that you do have a random texture on your surface. And that's probably where the origin of this misunderstanding comes about. We don't get a random reflectance of the light coming off, but the surface itself can be rather texturized. So, for example, if you suspect that this little material right here might behave like a Lambertian scatterer, you might put it inside of a tool and rotate the angle, right, and measure the amount of reflected light as a function of the angle to determine whether or not it follows this cosine theta dependence. And the reason it's important is because the backskins of our solar modules can quite often be Lambertian scatterers. And we have a certain amount of light that comes off at some angle here that will get trapped by total internal reflection inside of our modules. So if instead of having macroscopic pyramids right here, we had very, very small pyramids, still not sub-wavelength, but smaller features, for example, the texturization on the backskin right here, and it managed to scatter the light at a particular angle that got caught by total internal reflection. Macroscopically, we might be able to describe the scattering behavior of that surface as a Lambertian scatterer. But it's those waves, those rays that are bouncing off at those large angles that are causing the total internal reflection event. Okay, and so the notion of a Lambertian scatterer is important on the backsides of solar cell devices. We would obviously want to even change the scattering profile. We wouldn't want necessarily specular reflectance. We might want to maximize the amount of light reflected off at particular angles. And there's, of course, research being done to figure out how to make light do that. I'll show you one example at the very end of lecture, a paper that was just published in Science last week, as an example. And so these scattering centers off the backs of the rear sides of cells would operate more or less in the following manner. You'd have incoming light. Let's ignore front surface texturing for now. Let's just focus on the backside. And if you have some random, as they call it, a random reflector, a randomly texturized reflector on the back that reflects off in, say, a Lambertian fashion, you'll have some fraction of that light scattered off at an angle that is large enough relative to the surface normal that it is trapped by total internal reflection. And you don't only have to texture your backskin. You can also texture the bus bars. The bus bars are these little metal wires right here that are collecting the charge from each of the solar cells. And they're connecting essentially the front side of one cell to the back side of the next. If you want to think about it as the cathode to the anode, cathode to the anode, cathode to the anode, and stringing all these cells together in series. And this metal right here is just really shiny, and it's reflecting light right back out into space. What if we instead were to texture that metal so that when laser light shined on it, a certain amount would be reflected off at an angle and then caught by total internal reflection? And that's exactly what you're seeing right here. The light bounced here on a textured bus bar, bounced off of the glass more or less around here, halfway, and then got a second chance to enter the cell over here. Obviously, some of it is reflecting off so we can see it, but a lot of it's going in. And that little innovation right there, which was developed in the building right next door by Professor Ellie Sachs, can gain module performances somewhere on the order of a few percent relative. So that might not sound like a whole lot, but if you're a $100 billion industry, 1% is a lot of money. So it does add up. Yep, so that goes back to the total internal reflection. So there is a limit to all of this texturization. There's a limit to how much we can trap light simply by modifying or corrugating the surfaces to enhance the optical path length with these types of bounces using Snell's law. And of course, the general reflectivity equations. And a gentleman by the name of Eli Jablonovich, who's now a professor in Berkeley, calculated these parameters, I think, back in 1982, and came up with an upper limit to the optical path length. He said, after a long series of calculations, derived an expression for the maximum increase of the optical path length due to surface texturing, which was 4n squared. And that Jablonovich limit, to this day, is a pretty good litmus test for the ability of a material to trap light. So if you have silicon, for instance, with a refractive index of, let's say in the infrared, somewhere around 3.6, your Jablonovich limit is around 50, which means that you can increase the optical path length by a factor of 50 relative to the thickness of your material. If you have an organic material, which has a refractive index typically of around maximum 2, then that would be squared, 16, somewhere in that range. You can increase, probably on the order of 20, the optical path length inside of the material through texturization. So this is a useful parameter for those who are doing research in photovoltaics, the graduate students especially. And so I think the graduate students will have a question at some point on the Jablonovich limit. And so that's a useful parameter to keep in your mind. Let me touch upon a few other forms of trapping light. We've so far just assumed that light behaves like a continuous wave, doesn't interfere with anything, doesn't interfere with itself. Now we're going to discuss some anti-reflection effects which derive from the notion that light is a wave and can constructively and destructively interfere. What we have right here is a layer of another material with a refractive index, say N1, which is in between our N0, which is at air, and our N2, which is the absorber material, let's say the silicon. So we have a grading of refractive indices going from air, our anti-reflection coating, into silicon. And right over here we have a certain thickness D1, and over here we have a certain thickness D2. So what is happening in these two images? Let me show you with a little bit more clear figure coming from our beloved Wikipedia, and then go back to that other image right there. So what's happening is we have an incoming wave that for some reason is ignoring Snell's law. It's beyond me. But anyway, the wave is going in a straight line. Should be bending toward the surface normal, obviously. But we have reflections off of this interface and this interface right here, right? And because the thickness of this layer is in the order of lambda over 4, that means that the wave that's going in will be phase shifted relative to the wave that's reflected off the front surface, first by lambda over 4, then 2 times lambda over 4, in other words, lambda over 2, which means that the two waves are out of phase by lambda over 2, which means that they will destructively interfere. The peak will be at a trough, the trough will be at a peak, right? And so the two waves are going to be destructively interfering when they come out. If you add these two together, due to the wave nature of light, you get suppressed reflectance. And that's a really interesting property. You can begin varying the thickness of this layer and, of course, changing the nature of the reflected light. You can constructively interfere, if you like, and enhance the amount of reflected light as a result of this interference effect. Obviously, in most solar cells, we want to suppress reflection. And so we go to great lengths to make sure that this thickness, as well as the refractive index of the material, is optimized for a particular system. And so without going into the hairy math, to calculate this right here, it's definitely possible. It's definitely something that should be done. And I believe the graduate students have it assigned as the very last problem on the homework. But for a very simple kind of conceptual understanding that is wavelength independent, if we want to minimize the reflectance at a particular wavelength, let's call it at a lambda naught, which is the photon wavelength at the peak of the solar spectrum, we have to design the thickness of our anti-reflection coating to satisfy that equation right there. Essentially, lambda over 4, that's the phase shift we want upon one pass of the anti-reflection coating, so that 2 passes, when it goes through and then back, it's phase shifted relative to the surface reflected light by lambda over 2, divided by n being the refractive index of the material. Obviously, the frequency of light is staying the same as it goes from one material to another, but the wavelength would be changing. So that's why the n parameter appears right here in this equation. The T is the thickness of the optimal anti-reflection coating thickness. So just to give us a sense, kind of an estimate, and to give us some confidence in these engineering methods, what I'd like you to do is to calculate the thickness of an ideal anti-reflective coating. This anti-reflective coating right here on these cells, I apologize, they also have the metal on the front, so it's a little difficult to distinguish between the two. But in my right hand, this one, I have a piece of bare silicon, and you can see it's rather reflective. In my left hand over here, I have a piece of silicon with an anti-reflective coating, as well as some contact metallization on the front. So that's why you see those grid lines. But it looks very blue. It looks very blue because the cell is absorbing very well at the peak of the solar spectrum, which is in the yellow. Right? So calculate for me, what is the optimal thickness of an anti-reflection coating of silicon nitride, and we'll give it a refractive index of, say, 2.1. Let me see if those numbers make sense. So refractive index of silicon nitride, somewhere around 550. Let's call it 2, just make our life simple. And the peak of the solar spectrum we'll again call 550. So when we run the numbers quickly, what should that thickness be? Sure. So the N, the refractive index is going to be around 2 for silicon nitride. So we're going from air, which is around refractive index 1, to silicon nitride to silicon. And the peak of the solar spectrum, our lambda naught, which is the photon wavelength at the peak of the solar spectrum in vacuum or in air, is 550 nanometers. So what thicknesses are folks coming up with? Order of magnitude?
70 nanometers.
70 nanometers. That's almost spot on to the actual thickness, which is somewhere on the order of between 70 to 80 nanometers typically. You're telling me that something that is 1/1000th the thickness of my hair is deposited on the surface of this wafer and is absorbing all this light? That's pretty cool. And it's not absorbing the light. The anti-reflective coating is not absorbing the light, which is really important. We want the solar cell underneath it to be absorbing the light. The anti-reflection coating is enabling the light to be absorbed because it's suppressing the reflectance. The reflected modes at that particular wavelength are suppressed because of the destructive interference. That's cool. I really get a kick out of anti-reflective coatings. So they're 70 nanometers thick. And you gain quite a lot in terms of cell performance. I'll show you some slides to drive that point home in a bit. Okay, this is really briefly. I'll post these slides online so you can have access to them. If you use the matrix transfer method, as described beautifully in Gangchen's textbook, you can calculate the amount of light reflected across a broad spectral range for a given thickness of anti-reflection coating. So what we did right now was to calculate a suppression of the light at a particular wavelength, but you can also calculate with the tools that are available to you the reflectance of your particular device over a broader wavelength range. And that's pretty cool because now you can begin, say, multiplying this function right here against your solar spectrum and begin to calculate the total amount of light entering your sample and the total energy entering your sample. Equations, brilliant. The important thing to note here is that it really matters, right? This is silicon under glass right here, for example, typical solar cell material in blue, it's better than the bare silicon. Why is it better than the bare silicon? Silicon under glass. Glass has a refractive index or 1.5 or so.
Index matching, you go from pairs 1 to 2.3 and then to 2.6.
Yeah.
The difference is small between the classes.
Exactly. So if you recall that equation that described the amount of reflectance, there was that, what was it, n1 minus n2 quantity squared, right? So the bigger the delta between the n's, the bigger the difference in refractive indices between material 1 and material 2, the more the reflectance is going to be off of that interface. And so you can begin reducing reflectance off of a stack of light going both ways by grading the refractive index of the material. And that, of course, changes the reflectance in both directions. And so you get a reduction in the total amount of reflected light when you put the silicon under glass, because glass has a refractive index somewhere between air and silicon. And then you get a further reduction of the reflectance when you have an anti-reflection coating with a refractive index somewhere around, for this particular system, silicon again has a high refractive index. This used an anti-reflective coating of a refractive index of 2.3 of some thickness, probably somewhere around, let's see, maybe T greater, smaller, probably around 65, 75 nanometers, somewhere in that range. So what this is saying is that you can minimize the reflection of light off of the front surface of your sample by using an intelligent combination of the very first equation that we were exposed to in the class today, which was the reflected light as a function of refractive index, so essentially refractive index matching. And secondly, by engineering an anti-reflection or an anti-reflective coating, which oftentimes in the lingo of solar cell scientists, we call it an ARC, an anti-reflective coating. And those two things combined give us very low reflection off of the front surface. Probably 5% of our R&D cells that we make at MIT use these sorts of technologies, which are pretty standard in the industry. And you can see what the hit is, right? Let's say if I'm just using a bare material, if I'm getting 30% reflection, I'm getting a 30% drop in the current output of my device. That's pretty significant. So these are simple ways to improve performance of devices. If you want to become fancy and actually trace, do what's called ray tracing to calculate the path of light through a medium, there is software available that will take all of what we've discussed today and calculate it for you. So you don't have to walk through the expressions that we just walked through. It is easy. In other words, you plug something in, you get some ray traces, you can calculate reflectance and so forth, transmittance, but it's as smart as what you put into it. It's really important to understand the fundamentals behind any simulation software, because you will get out of it what you put into it. You will not be able to pick up on obvious things that you might have, for example, double-clicked on this little material here and defined the real component of the refractive index completely wrong. And you might not notice it, you might not pick up on it if you don't have some good intuition, which is grounded in the fundamentals. And so it's important that you understand what we've presented today. It's important you understand the reading and, of course, do the P set as well to really drive those fundamentals home. So to kind of put a big umbrella over the entire lecture, light management ensures that the absorptance is high. The absorptance would be essentially the amount of light getting absorbed inside of the material normalized by the amount of light going in, so 1 minus R. So we have, we want to ensure that light enters the absorber. We want to minimize reflection. We want to ensure good light trapping inside of the absorber as well. The absorber being the material, our photovoltaic material, the one that's absorbing the sunlight and ultimately going to be generating the charge. So we call the absorber. So we want to ensure good light trapping inside of it. We want to ensure that the maximum amount of light gets trapped inside. We want to maximize the optical path length within it. And we want to minimize reflectance off the front surface. There are fancier ways of light management as well that don't involve light trapping necessarily, but light manipulation or even semiconductor manipulation. You can, for instance, change the wavelength of the incoming light. One very simple example of this is when you shine, say, for example, red light on a phosphor, and then it glows green in the dark. Right? That's a wavelength change. Maybe not red. You'd probably have to shine blue to have it glow green. That's an example of a spectral down converter, where it's taking a higher energy light and converting it into lower energy light. Likewise, there are folks out there trying to do spectral up converters, where they take two lower energy photons and somehow convert that into a higher energy photon. Right? And so since our absorption coefficient is dependent on wavelength, if we're able to shift the wavelength of the light around by engineering materials near the surface, we can enhance absorption as well. That is a valid form of light management. It has additional benefits as well. If we can eliminate the longer wavelength stuff out here, which is heat, performance of most solar cells suffers when they get hot. And we'll learn why that is about 5 or 10 lectures from now. And so if we manage to do spectral upconverting or reflect that long wavelength light away from our device, we can improve performance there as well. That's another form of light management that doesn't necessarily involve light trapping. Okay, so again, I wanted to really emphasize that light management is necessary in devices. This is no light trapping, the blue curve, and with light trapping being essentially just an engineered coating on the backside of your device. If light's coming in through here, I've engineered a coating on the back to reflect the light back so that it gets a second bounce through the material. I've engineered the front surface, texturized it so that we have not only the benefit of 2 bounces, double the chance of the light going in, but also the Snell's law working in our favor and increasing the optical path length. And so all told, the one reason why this boost is so big right here is because I'm increasing the optical path length, the effective optical path length, relative to the thickness of my material. And as a result, I'm getting a much larger current output. I'm generating many more free carriers inside of my material. I'm absorbing much more light inside of my material. Just a very simple calculation versus cell thickness. And obviously, the thicker and thicker and thicker you go in your device, the less important this becomes. Because the less important light trapping, I mean, you have entire thickness that it can absorb the majority of the light in one pass. But if you have a thinner device, it really begins to matter. Once the thickness of your device starts approaching the optical absorption, or 1 over the optical absorption coefficient, which is the extinction length, then it really begins to matter with the absorption length. Light trapping can still matter for thick devices, though, because if you manage to make the light essentially refract or bend, if you will, so that it travels near the surface, the distance that those excited carriers have to travel to be collected is shorter. And so you can get an additional benefit from thicker devices by engineering light trapping as well. Okay. Any questions about this? This is kind of important. This is why we spent all this time in lecture today talking about light management, is because of this plot right here. That's why. I just wanted to show you a cross-section of a very high-efficiency device. This is one of the highest efficiency silicon-based devices that are out there. And we have these so-called backside mirror, which is really just a layer of dielectric material, typically, that reflects the light off of that interface using the equation that we saw at the very beginning of class, the R equal to open parentheses 1 minus, or n minus 1, quantity squared, divided by open parentheses n plus 1, quantity squared. So that's benefiting here from the change of refractive index going from your silicon to that dielectric material on the back. They definitely take good advantage of it. Where you have your metal, you're going to be absorbing the light, or you have a higher probability of absorbing the light than you would if you had a dielectric semiconductor interface. So the device design can get pretty complicated for these super high efficiency devices. And they're worried quite a bit about light trapping, other things as well.
How efficient is that one been?
This one right here, in the lab, 24.2%. In commercial production, 22% and change, 22.4, I think. Just to throw some last things out there, since we're 5 minutes to closure. Snell's law assumes that there's no phase shift of the light as it transfers from one medium to another. If you introduce a phase shift, this is just a paper published in Science last week by our friends over at Harvard, Federico Capasso. If you introduce a phase shift of the light as it goes through one medium or another, now you can start doing some fun things. If you introduce a constant phase shift gradient throughout the surface of a material, let's say right here, then you can cause each node, each point within your material to lag by an increasing amount. And so that your wavefront now bends right? You can think of these as kind of a Huygens wavefront forming as a result of these small nodes here. And if you can tailor the phase independently at each one of these points, you can cause an increasing delay as you go across, and that will cause the light, essentially, if you trace through the points of maximum intensity, say the pink, you'll see that the light is bent. And that's pretty cool, because now we can, in principle, if this is hot off the press, and of course there's a whole flurry of researchers out there trying to figure out how to use this to our advantage, but with anomalous refraction, in principle, now you can tailor the angle at which light bends inside of the material. Perhaps you can even exceed the Jablonovich limit inside of the material, right, as a result of this. And so it's really exciting. There's stuff coming up every day. This is the point. There's stuff coming out every day on light trapping and light management. Mostly it's for photonic devices, but they can be transferred over into solar cells as well. So it's good to keep your eyes open. And another example of the photon up-down converters, there's recent reports in SPIE, a lot of interest in the optics community. There was a TR35 award given to a person who's studying this topic. So it is as well a very exciting and up-and-coming field. Again, the opportunities there of manipulating light are large, are vast. So the laws, if you will, that constrain us, that we've discussed today in class, don't let that constrain your thinking. That's my final message. Thanks.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Why don't we go ahead and get started? What we're going to be talking about today is what happens after that photon gets absorbed, right? So we spent a great deal of time in our last lecture talking about light absorption, the interaction between light and a semiconductor. Now we're going to talk about what happens once that light is absorbed. So we're in the fundamental section. We're right here. Later on, we'll get into the technologies and the cross-cutting themes. As we go through the fundamentals, I'm going to attempt to relate those fundamentals to real solar cell technology, right? So you're not left kind of floating, wondering why it is that we're studying this stuff, but you're really seeing the connection to solar cell devices. So first off, we remind just everyone of the broader picture that the conversion efficiency, the ultimate performance of the device, is defined as the output energy versus the input energy. And for most solar cells, this breaks down into the inputs and the outputs, the input being the solar spectrum and the output being the collection of charge. And there are multiple processes that occur here in the middle. Light absorption we talked about last time. We're going to be talking about charge excitation and charge transport today, mostly charge excitation. So we're right here, and we're going to be marching steadily down toward the right over the next few lectures. And let I remind you, everybody, that the efficiency of the device is the product of each individual efficiency of each different step. So if anything is going wrong here, it will be limiting device performance. And the image you should definitely have in your mind is of that bucket, with each plank representing a different component of the device, perhaps a different physical process, or perhaps a different physical component of the device itself. And whatever is the poorest is going to be limiting overall performance. Your efficiency is going to be flowing out from that low plank, and you will have a low efficiency device. So the art of making a high efficiency solar cell is really understanding everything that goes into the physical processes, but also the devices. And that's why we break it down like this. We have the physical processes, and finally we get into some of the devices and the architectures and the manufacturing methods. So learning objectives today. Oops. That was a little bit of a typo. It's not the solar resource. We're talking about charge excitation today. We will be talking phenomenologically how this thing called a band gap forms. It's a very important physical concept. We'll lead off the lecture with it and then very quickly go into applications so that you see why it's important, returning back to the fundamentals, how it actually forms, going back and forth until we have a pretty solid understanding. From the background surveys, I understand that about 50% of you understand what a band gap is. So 50% of you may be a little bored or a little entertained at my hand-wavy explanations during the first part of class. I encourage you to think about the band gap from the perspective of the solar cell device, because this is probably not something you've done before. You've probably understood band gap from the perspective of a semiconductor device that's packaged in the dark, perhaps in a little gadget like this, but not something that's exposed to light with the addition of a generation current, or at least not in detail. So I welcome you to think about that as we go through the explanations in the beginning of class. Then we'll describe how optical absorption in semiconductors represents the transitions of charge in an energy band diagram. In other words, if we imagine a given space of the semiconductor device, say a surrounding of a given atom, and we imagine that different orbitals, different electron orbitals will have different energies associated with them, we are going to be talking about how light gets absorbed and transitions electrons between those different energy orbitals. That's important because then we'll be able to calculate the fraction of photons lost, not absorbed, by a given semiconductor material. We'll be able to calculate the fraction of incident solar energy that is lost as well due to a phenomenon called thermalization. And finally, we're going to be able to plot efficiency versus band gap and denote specific materials on it. In other words, we are going to be doing our first higher level efficiency calculations for a solar cell device by the end of today's lecture. And the idea is to expose a little bit on the technology side as well, so that you have an appreciation for what's up and coming in the field, what are some of the ways to enhance the performance of solar cell devices. So band gap, very, very basic description. The way if you've never been exposed to band gaps before, the reason it's important is because the band gap is going to define what color, what portion of the solar spectrum that material absorbs light most efficiently. How a band gap forms is related to the atomic structure. Think of bonds as essentially why stuff is tough. If the mechanical engineers in the room, if you remember linear elasticity, those bonds are what are essentially forming those springs between the atoms that are keeping the material from flying apart. There is also a very interesting property here that if you have a bound electron, it's usually not moving very far from that atom. It's usually in a very localized electronic state close to that atom. So if you were to apply, say, a resistance meter, an ohm meter to your device to measure the resistance across it, and you had just bound electrons, you would measure a very, very low current passing through that material because there would be very few free charge carriers to move in that applied field. When you apply the two probes, and there's a little battery in here that applies a field across the material, you wouldn't be able to measure much current flow because there wouldn't be too many free electrons to carry that current. So the bound electrons essentially enhance the strength of the material, but it doesn't help us from a semiconductor point of view. What we need are excited electrons, and excited electrons are why materials conduct. So let's imagine we have a bond. For example, in this material right here, these gray lines are really two electrons that are covalently bonded, essentially one electron from each little black circle representing a carbon atom. And each electron associated with that carbon atom is shared with the other in a covalent bond. For the chemists in the room, more precisely, you have sp3 hybridized orbitals in this diamond cubic crystal structure. For everyone else, these are shared electrons in a covalent bonding configuration. Now, if light comes in with enough energy, it can excite an electron from that covalently bonded state into an excited state where it can then roam freely throughout the lattice. Right? And that's the nature of charge excitation. So the big question that we have to ask ourselves is, what color of light will this material absorb most effectively? Will those electrons in the covalent bonds absorb light and be excited into a state where they can roam freely around the material and ultimately conduct electricity? Okay, so the answer to that question is not simple. Understanding how a band gap forms can be an entire semester of quantum physics, but what we're going to do is do it in a three-step approach. Simple, very, very simple explanation that hopefully everyone will get. The next most simple explanation, which hopefully 80% of you will get, and then perhaps a more detailed explanation that only a few of you will get. But the idea is to really progress in levels of explanation. So let me go back one step. Yeah, the band gap energy can be most simply understood as a finite amount of energy needed to excite a highly localized electron into a delocalized excited state in a semiconductor where it can move around the crystal. Okay, so this is the description of the band gap, how a band gap forms, that you'll see in many chemistry textbooks, and I like it because it's something that you can really grasp and understand. We have to start with the simple premise that electrons are a type of particle called a fermion. What is a fermion? Let's refresh our basic physics here. What means a fermion? Spin 1/2, and it also means, can two fermions occupy the same state? No, they can't. Bosons can, but fermions cannot. And so what happens when you put two fermions together in a system? And say we have discretized quantum states. We begin filling up from the bottom up, right? Typically. So the lowest energy states get occupied first. You have, for example, spin up, spin down in your s orbital. And then you begin populating the next electron orbital. Once that's filled, you go to the next one and the next one. So if we have one atom in isolation, the easiest example is that hydrogen atom. For those who took quantum mechanics, you actually calculated the energy of the bound electron there in the ground state of the hydrogen atom, around 13.6 eV, right? So imagine now you take a silicon atom, or a carbon atom, or something else, a little bit bigger, more electrons in its structure. So you have the core, say the 1s orbital filled, and you start progressing outward, right? 2s, 2p, and so forth. And so you begin filling up the orbitals. Let's see atomic separation. Let's imagine that we have our atoms infinitely separated. So we have just one atom in the middle of an infinite lonely space, one atom. And we would have discrete energy levels corresponding to the different orbitals around the nucleus. Now imagine the atom is no longer lonely. It now has a partner. And you bring those two atoms closer and closer and closer together. That's this D getting closer and closer together. What happens? Well, electrons are fermions, right? They don't like occupying the same electronic state. So first, the first shell that's going to, quote unquote, see each other, the first electron shell that will interact is what? Is it the outermost or the innermost? Outermost, right? Because they're the closest together. So you're moving the two atoms closer together. That outermost shell will begin to, quote unquote, see the other atom. And those electrons will say, hey, you're occupying my state. And what will happen is they'll begin splitting in energy level. And that's what you see right here. What this is representing is not just two atoms coming together, but a multitude of atoms coming together. And we have to really imagine, for example, in most matter, we have something on the order of 10 to the 22, 10 to the 23 atoms per cubic centimeter, right? So atoms per cubic centimeter. Fun math, just total aside, if anybody talks about teletransportation, think about the number of atoms in your body and assign an x, y, z coordinate to them, and then calculate the amount of data in terabytes, and then calculate our Ethernet speeds and try to figure out how long it would take to transmit that data to the other side. Anyway, so this is to give you an impression of the density of atoms within the cubic centimeter. So you have a lot of atoms coming together. Even though the electron wave function can be highly localized, they still interfere with each other. There's still enough atoms coming together that you have this interference. And it's not just two electron states, but many of them that are splitting now, that are forming a band of states, because no two electrons can occupy the same energy level as these atoms are coming together. Now, as they become closer and closer and closer, it's not only that outer shell that begins interacting, it's the next most outer shell, this one here, that begins interacting, and finally another shell and another shell. Right? And so at some equilibrium distance, the equilibrium distance here defined as the attractive potential between atoms. There's an energy gain by forming that bond. And the repulsive force of the nuclei, there are large concentration of positive charge in the nucleus, and if you try pushing them too close together, they'll repel. This balance of forces, the attractive potential due to that bond formation, the repulsive force due to the nuclei, results in an equilibrium bond distance, d, shown here, it's this dotted line. And at that equilibrium bond distance, some of the orbitals will be forming bands, and other orbitals will still be discrete. Namely, the core orbitals will still be discrete. The outermost orbitals here will be forming bands. Now, an interesting thing happens when it just so occurs in this, say, for example, in this system right here, this shell is filled, this shell is filled, this shell is completely filled, right? And let's imagine that this orbital exists, but it's unpopulated, right? You ran out of electrons, and you started filling in the orbitals of this atom over here. You had enough for this orbital, that orbital, that orbital, but then you ran out of electrons. You didn't have anything more, and this band of states was empty. So the band of allowed states exists up there, but it's empty, and this band right here exists and it's filled. These core states exist and they're filled as well. So the action is really happening right here. If light comes in it's going, if say visible light comes in, it's probably going to excite an electron from this filled band right here to somewhere in this unoccupied band up there. And this gap right here is an interesting thing. There is no stable electron orbital. If you were somehow to take an electron with that given energy, this energy here, from the vacuum and stick it inside of the system here, it would quickly decay into a stable orbital. So this is a prohibited band of states. There is no stable orbital for that electron to exist at that energy, and hence we call it a band gap. The reason band gaps are interesting is because different materials have different, or can have different size band gaps. Some don't have a band gap at all. Most of those don't have a band gap because you have a band of states like this one that's partially full. Let's imagine we have 3 electrons in this band right here, 1, 2, 3, then we have these other 4 empty states above it. Right? You have a partially filled band. And let's imagine instead of just having 7 states within that band, we had a multitude of states within that band, almost too many to count. And now with the slightest of energy, we could excite an electron from this state into that state plus little delta, right? That would be a metal. Now, if we had a really big band gap, we wouldn't be able to absorb much light because you'd need a large amount of energy to excite across that band gap. And that would be an example of, say, glass, where light would come in. Most of our visible spectrum makes it through the glass, and that's why we see to the other side. And diamond as well. OK, so let's review. An atom in isolation has discrete electron energy levels. And on this diagram right here, it's represented with this D, the atomic separation, being way out here. We have discrete energy levels. And that we can remember from our basic physics, especially the hydrogen atom. As atoms move closer together, as in a crystal, where you have a regularly repeating arrangement of atoms, the electron wave functions begin overlapping. And since electrons are fermions, meaning that the 2 electrons can't occupy the same state, you have a splitting of those energy levels, forming bands. And you can see the splitting as you move from right to left, as you move from further to closer on these diagrams right here. First starting with the outermost states, the most valence of electron orbitals, and then slowly moving into the core states as well. And the gap between bands, denoting an energy range in which no stable orbital exists, is called the band gap. Sometimes you'll see it all written as one word. Sometimes there'll be a space between the band and the gap. Any questions so far? OK. So now this explanation should be relatively straightforward. What I want you to log into your RAM, because we're going into some more detailed explanations, and I want to set a marker, a flag, so we can come back here afterward. And even if you're lost with the subsequent explanations, you still get this one, right? So remember these 3 points. Maybe make a note of them in your notes. And we're going to move on to a few more explanations here. OK, so another way of looking at this, which really builds on the folks who have had a more advanced physics backgrounds, is that the wave function of an electron inside of a crystal. If you recall the wave function of an electron in free space, we have what is called the plane wave equation for the electron, right? It's this regularly repeating, nice, stable function. Now, if we introduce that electron into a crystal, it's almost like an infinitely repeating system of atoms, right? And so you could envision that you could describe the wave function of that electron as a combination of a plane wave but perturbed by that locally repeating potential from the atomic nuclei. And let me be more specific about regularly repeating potential. What I mean is that you have a series of nuclei here, and if you imagine the electron potential around these nuclei, there is a propensity for the electron to be bound by the atom, right? And so as it's moving along, instead of just a free plane wave, it's almost like driving along a bumpy road, a bump, a bump, a bump, a bump. Right? And so the wave function of the electron can be described as this combination or product of the wave function of a plane wave envelope function describing the electron localization. So you have this localized function here and the delocalized function describing the plane wave behavior of the electron as it moves through space inside of the crystal. Now, what we have is an easy way to describe this mathematically is we make an approximation. Instead of describing this potential in detail, the easiest way to do this is to describe this square well potential. We have a so-called chronic penny idealization of the repeating Coulombic potential. It's easier to solve numerically. And then essentially what we do is we solve Schrodinger's equation for two possible solutions. One is for the electron wave function centered on the atoms themselves. So that would be the bound state. And the other is we solve the equation for electron wave functions centered between the atoms. So essentially in the unbound state right here. Which do you think will have the higher energy level? In between the states, right? Because if the electron wave function is centered over here, it's further away from the positive charge of the nuclei. You need more energy to put it into that position. It's an unbound state, but it's also at a higher excited energy level. Whereas if it's bound around the atoms themselves, you would have a lower energy state. And this delta of energy levels between the bound and the excited states represents the band gap of the semiconductor in this simple approximation right here. Now you can take that one step further and say, well, gee, if I could solve that in one dimension, in a very simple case, why don't I put a three-dimensional structure in place, such as a real crystal, and then solve the Schrodinger equation? Then sure, you can do that. You can definitely do that. It becomes much more complicated solution numerically, but the general principle stays roughly the same. You can add several more tricks and bells and whistles. And of course, I would probably emphasize that the solution could either be done numerically, or you could use the symmetry relations of the crystal to develop a very simple expression of the crystal, minimizing the redundant directions inside of the crystal, collapsing it down into the bare essential to describe that crystal structure. And we would have some uniform energy space that looks, for example, represented by this yellowish surface where you'd have an isopotential inside of your crystal structure. So these are different ways of looking at the band gap inside of a semiconductor crystal. If you're really interested in for the advanced reading, I would definitely suggest this book called Fundamentals of Semiconductors by Professor Peter Yu, now retired at UC Berkeley. Very nice explanation, uses an elegant application of group theory to derive the band structure of a semiconductor in detail. So let's hop back to this one real quick. And Ashley, yeah?
I was just curious if you could tell us the name of the equation that was at the top of those.
Sure.
Is that the
Sure.
function or not?
Yeah, absolutely. So what we're describing here is essentially the e to the ikx or e to the ikr, essentially describing that periodic potential, and then in essentially an envelope function. So yeah, that would be the wave function that would be introduced into the Schrodinger equation. So let's go back to here really quickly because I don't want to get us lost in the weeds. I want us to focus on the main concepts at hand. Let's, from an engineering point of view, given this formation of bands inside of real materials, as the atoms are coming together and forming crystals, we can envision a few different scenarios. Let's focus on this band here and that band here and the space in between them, the band gap. And let's assume that we have this band here either completely filled or partially filled, and talk about what happens in three different extreme scenarios. In one case, when we have the band partially filled, we have what is known as a metal. And the reason this case is interesting is because a very small amount of energy is all that it would take to excite an electron and make it move around the crystal. As a matter of fact, a metal has what's called an electron C that serves to conduct electricity at room temperature and even at very, very, very low temperatures. Semiconductor, on the other hand. Now, a semiconductor has a finite band gap, and we'll get to this in a minute. Let's start with the insulator because that's a more easy to understand case. If the band gap is very, very, very big, then a large amount of energy is required to excite an electron into an unbound state so it can move freely across the crystal. And as a result, you're not going to have a very large population of electrons up here. The photoexcited carrier population, meaning the population of charge carriers, electrons, that are excited into here from light is very small. And the thermally excited carrier concentration, just from background thermal energy, KT, Boltzmann's constant times temperature, that energy is also going to be insufficient to drive electrons across this band gap. And as a result, you will have a very, very small population of carriers up here. And this will be an insulator. because you will have very few charges to transport current. Right? If you apply a potential across an insulator, you will not have very much current flow. And that's the principle of insulating materials around, say, wires. Actually, this isn't a semiconductor. This is a polymer. But if we had, for example, glass or diamond, that would serve as a nice insulator as well. Now, a semiconductor material is somewhere between a metal and an insulator here, in that the band gap is now shrinking. The band gap is small enough to interact with light, typically. For example, this little piece of silicon, which I'll show in detail in a minute toward the end of class, it doesn't look clear like glass does. It looks opaque. And that's because it's absorbing photons in the visible spectrum, but it's letting some of the infrared photons go through it. Some of the very low energy photons can go through the material because those photons have insufficient energy to excite carriers across that band gap. So we have a semiconductor material defined here as having a band gap. That band gap defines the energy of the light that is most efficiently absorbed. And any photon with energy in excess of the band gap can also be absorbed by that semiconductor. Any questions so far?
Are there any natural materials where the spacing of the bands is such that 3 bands are active, or is it always just 2 bands which are active?
Interesting. So the question is, are there more bands above here that you could excite into? Absolutely. So as you can envision, back here, for instance, you could continue drawing more and more and more bands. They're unoccupied, but they exist. And as the atoms come closer and closer together, those begin interacting as well. And so when you look at, in a few lectures, we'll look at a band diagram of a semiconductor, and we'll see all the occupied bands and all the unoccupied bands. And you can excite into any one of them if you have the right excitation condition. Let's put it that way. Any other questions? Yeah.
I'm having trouble seeing the chemist description along with the physicist description along with this slide altogether. Like, how does, once it's in the crystal structure, it's got all its, and it's in its lattices and everything, how does that look in this picture? Where is that in this picture?
Sure. So this one here, let me describe the axes because that might make things a little easier to understand. In the vertical axis here, we have energy. And that's the same axis as we have right here, energy. In this axis right here, we had interatomic separation. So this was meant to demonstrate what happens when we bring atoms closer and closer together. In this description right here, this is an unlabeled axis. It could be x, real space, for instance. Why do we plot an x in this in the x-axis? Why do we plot in real space? Well, sometimes when we talk about solar cell devices, we're talking about bringing charge from deep within the device to the front surface where the contact is. And so we'll want to talk about the flow of charge in real space. So that's oftentimes why you see in these band diagrams for solar cells, you'll see E versus X versus real space. Now, let me show you what these two levels here represent. This is the top of the filled band and the bottom of the empty band. And those correspond over here. I'm going to use the mouse now because I'm going to be stretching. Let's imagine that this level on down was filled, and that this level up here is empty. So if I may, these are all filled, and this one here is empty. Going to take a little bit. There we go. All right. So now this band is going to be filled because we're really looking at the equilibrium interatomic separation in a crystal. We're looking right here at this D. That's the spacing right now of those atoms inside of that piece of semiconductor material, inside of that silicon. So what we care about is this right here. And this would be the top of the filled band, and this would be the bottom of the empty band, corresponding to the top of the filled band right here and the bottom of the empty band right there. So that's how it all fits together. This diagram here can get kind of confusing when you look in the abscissa, essentially in the x-axis, because you're thinking in terms of real space. Well, it is real space, but you're bringing atoms together. It's really meant to be a phenomenological tool to describe how band gaps form. This diagram over here, we're now starting to get into the engineering diagrams that can help explain how solar cells work. And from here on out, we'll be abandoning that chemist's diagram and simply using this one, because we assume that we're not applying a significant strain to our semiconductor material. To get deviations, significant deviations here, we'd have to apply strains of several percent and probably result in fracture of our semiconductor before we ended up changing that interatomic distance. You could also heat it up. Yeah, it's another way of introducing strain, thermal strain, but not mechanical. Okay, so did that help answer the question? Okay. So the second point here, we wanted first to describe phenomenologically a band gap and understand how that works. Secondly, we want to describe optical transitions in the semiconductor and understand how charge carriers, in other words, how electrons on an energy band diagram are moving around. Why do we call electrons charge carriers once again? Remind me from this diagram here.
They carry charge and they move around.
Exactly. That's why. It's brilliant. I just want to make sure that it's those two things are synonymous in people's minds, that we're not getting caught up on the language. Thank you. So again, charge carriers, electrons meaning free electrons, unbound electrons, not any electron, not the ones down here, but the ones that are excited. Okay, so let's go back to lecture number 2, I think it was, where we talk about the duality of light. It's a wave and a particle. Or can be thought of, can be described mathematically as waves and particles. We've, in last lecture, when we talked about light and the interaction of light with materials, we referred to light mostly as a wave. This was very easy for us to describe interference. It made it convenient to do the homework problems, especially for the graduate students, the last problem. That was a lot of fun. But now we will be talking about light in terms of discrete quanta of energy, because one photon is going to be absorbed by an electron and excite that electron into another state. Right? So now we think of the photon as having a certain energy defined by the wavelength of the light. And that energy is going to be given to the electron, which will then be excited inside of our semiconductor crystal. So what happens? Well, we have our sun. Here we have our semiconductor crystal. Again, I'm representing it in terms of E versus X. I'm saying that these states here are filled. And these states here are mostly empty, and these are mostly filled, mostly empty. And this is my band gap right here. I'm plotting E in the ordinate and X, real space, in the abscissa. And again, X because ultimately we'll be looking at the cross-section of the solar cell in X and describing how charge gets extracted from the device. So that's where we're going to be using X in this axis. Now we have sunlight here outside of our device, and it's going to be shining light onto the semiconductor crystal. So what happens? Well, we know intuitively that charge should be excited from a bound state to an unbound state where it can move around the material, but not all light serves this function. If we have a photon that has an energy above the band gap energy, so E photon, meaning the energy of the incident photon, is greater than E gap, the energy band gap, then we'll have an excitation of charge. We'll have an electron taken from somewhere here, brought up to a higher excited state, and it might come to settle down at the bottom of that band of states that is allowed, just a settling, if you will. But if our photon energy is less than our band gap, we won't have this process occur. Instead, we'll have the light going straight through it, right? And this is brilliant because you can begin to understand the behavior of many solids in this way. Let's take glass, for instance. How many of you have noticed that you never get sunburned when the windows are up? But you get sunburn when you forget to put the windows up, when you're driving around and your hand's sticking out of your arm's sticking out, and you get that nice trucker's tan. That's because the ultraviolet photons have enough energy in glass to excite electrons across the band gap. So the ultraviolet photons gets absorbed by the glass, but the visible photons instead are coming straight through, much like this. Now, glass has a very large band gap. Now, silicon, much smaller band gap. And in that case, in the case of silicon, even the visible gets blocked. So silicon would make a really crummy window. But it makes a really great infrared window. So if you're detecting infrared light and want to block out all the visible, you might consider sticking up a filter made of silicon. And that's regularly done in laboratories. So you can begin to understand how light interacts with matter, with solids, using this energy band diagram, and ultimately how these optical absorption spectra come into being. So we studied these optical absorption spectra in our last class. We just took them as a given. We didn't question where they came from. Now we're going to be focusing on this so-called turn-on energy or turn-on wavelength. Remember, wavelength and energy are interchangeable. I've written down below here the energy corresponding to a given wavelength, around 2,000 nanometers. We have an energy of around 0.62 eV. At around 200 nanometers, we have an energy of 6.2 eV. Since one is the reciprocal of the other related by hc, it's only natural that if we change one by an order of magnitude, we're changing the other by an order of magnitude, but in the opposite direction, right? So we're wrapping our minds around this interchangeability of wavelength and energy. That's important because we'll be referring to them very naturally as a photon either having a certain wavelength or a certain energy. And you notice that there are certain turn-on energies, right? So energy is increasing in that direction there. So as we go from infrared to ultraviolet, the energy of the incoming light is increasing. And if the energy is too low, the semiconductor crystal just won't absorb. The absorbance is 0 or very, very small. It doesn't even appear on the log plot here. And as we begin increasing the energy, suddenly there's like a turn-on. The semiconductor begins to absorb that light, and you begin to have this process occur right here. Right? You begin to go from that red light that went straight through the material to this blue light example here where we have absorption event. Yeah?
I think probably a minor question, but where does the energy go that gets released when your electron settles back down to the band?
We're going to get to that.
Okay.
We're taking it step by step, but it's a really good question. You're one step ahead of me. We're going to be describing the actual shape and character up here because this is equally important for the functioning of a solar cell device over the next few lectures. But that gets really complicated. So for now, we're going to just focus on this turn-on energy, and we're going to make some assumptions from here on out that the semiconductor doesn't absorb, and all of a sudden, boop, it absorbs, and the absorption goes high, right? It begins absorbing all of our light for our purposes of our homework assignments. So again, just to put this all into one big picture so far, we have the case out here where very little light is absorbed by our semiconductor. We have the case of glass, light coming straight through it, visible light rather. Because the incident photon energy is less than the band gap, there's insufficient energy to excite into the conduction band. Now, as we transition from a photon energy less than the band gap to a photon energy larger than the band gap, we can begin exciting electrons or charges across the band gap, and that's why we get absorption inside of our semiconductor materials. Any questions so far? Okay, good. Everybody's still with me. We're going to now calculate the fraction of photons lost, not absorbed, by a semiconductor material with a given band gap thickness and reflectivity. And this gets to Ashley's question right here. So again, we ran through a thickness estimate in class the last time. And we assumed for a semiconductor, I think it was around 800 nanometers. For gallium arsenide and silicon, or maybe it was a little less, somewhere around 550. What was the thickness necessary to absorb, say, 90% of the light at a given wavelength? And we, in the back of our minds, had the solar spectrum here as a reference point to begin visualizing the number of photons that occur within each of these delta wavelengths down here. Essentially, what portions of the spectrum really matter? Obviously, you're not going to optimize your solar cell to absorb light way out here because there's really not too much of the solar spectrum way out there. You're probably going to optimize it somewhere around the peak of the solar spectrum or somewhere near there. So we walked through that in the last class. I want to have that in your RAM as we move forward. We want to calculate the fraction of incident solar energy lost to this thing called thermalization that Ashley was mentioning before. We have, in this simplified diagram right here, an electron popping up to a higher energy level and then settling down to the bottom of this conduction band, we call it, this band of states that's empty right here, or largely empty. And this settling down to the bottom of what is this mostly empty band of states is a process called thermalization. And it occurs, well, because there are a series of states. The electron can very easily move between them by emitting phonons, or lattice vibrations, or heat. And very quickly, that electron will settle down into what is called, or referred to as, the conduction band minimum, the minimum energy level within the conduction band. And this little arrow shown in red right here has a component in the y-axis, in E space here, which is a finite energy. We can quantify that. That thermalization loss right there is the difference between this energy level and that energy level of the electron. And so that's the thermalization loss. That is another type of loss of a semiconductor crystal. So we've discussed two so far. We've discussed non-absorption of light, There are certain long wavelength, low energy light that goes straight through our material and doesn't get absorbed because the photon energy is less than the band gap. And the second major loss mechanism is when we have too much energy of that incoming photon. We have an excitation of a bound electron into a very highly unbound state, and then a quick loss of that excess energy due to a process called thermalization. Any questions so far?
You said that the thermalization can result in heat being released or in photons.
Mm-hmm. Yep. So not the prime energy that we extract from the solar cell of electricity. In principle, if you could develop some clever way of extracting that heat, perhaps by slapping on a thermoelectric device in the back of your solar cell, then you could extract that energy as well. So there's a potential to recover that heat. It's not total loss, but from a mechanical engineering point of view, if you think about the thermodynamic efficiency of a Carnot engine, where your T high is this, and your T low is your ambient temperature, that delta there really doesn't look that good, right? Yeah, it's really tiny. So you have to think of a more clever mechanism, perhaps through a thermoelectric device or some other mechanism to extract that extra thermalization loss. I wanted to, so what we're doing is we're taking the simplest picture and then adding layers of complexity. And you'll hear me stumbling over my language as I sanitize it in my head to remove all of the complex techno-lingo and reduce it to its essence. And so right now I'm going to add one more layer of complexity and ultimately build up to the point where I can feel conversant again. We have incoming light not exciting the electron all the way up to there from the top of the valence band, but typically somewhere within the valence band, not really at the valence band maximum or the maximum energy level within the valence band, these being the filled states. So this is a more realistic representation of charge excitation. We have an electron being excited up, and this little H plus that's right here. Who did the reading and knows what that H plus represents? Yeah. A hole. So what is a hole? Well, it's just what it sounds like. It's the absence of an electron. There used to be an electron here, now it's up there. It left behind a hole. An easy way to think about a hole is if you're in a big traffic jam, bumper to bumper, something bad happened up ahead and backed up the traffic. Now imagine just removing one car from that highway. You've created a hole. So that electron that used to be, or the car that used to be behind that hole moves forward, and the car that used to be behind that one moves forward, and the car that used to be behind that one moves forward. So 3 cars moved forward, and the hole moved backward 3 places. Right? So you can either describe the dynamics of the system as n number of cars moving forward, or one hole moving backward n places. It's much simpler from an accountability point of view to be talking about one quasi-particle, a hole, rather than talking about n cars moving or n electrons moving. So when we talk about this hole right here, thermalization is going to drive this electron to the lowest energy level within the conduction band. And it's also going to drive the electrons above the hole essentially to fall down into the hole. In other words, the hole is going to move up to the top of the valence band. Yes, question?
Why isn't the hole originally created at the top of the valence band?
Well, it really depends on what's called the it depends on what's called the matrix element of the absorption process. In other words, what electrons have the largest capture cross-section for that incident photon. And it is a probability distribution function, so some of those, you will get some electrons further down from the top of the valence band absorbing light, as well as some of the electrons right there at the tippy top of the valence band absorbing light. So I'm representing, say for example, a typical case where you have an electron that's not right at the top of the valence band, and certainly not deep in the core level, but nearish enough to the top of the the valence band, absorbing that light and being excited across. So in reality, this is meant to be an arbitrary scale here, but more representative of a whole process. And to think about this in a more realistic sense, what you would do is you'd think, okay, I have this incoming photon, and there's a certain probability distribution function that represents the probability of absorptance by different electrons in my system. Which one is going to absorb the light? Well, let's roll the dice, do a Monte Carlo. Okay, that one absorbed it this time. That one got excited up. Okay, another photon with identical energy coming in. Which electron absorbs it? That one, right? So that's the way I would say it really works. This is a simple representation on the, say, a lecture slide. So we have the hole going up and the electron going down. Both particles are relaxing. Right? So the electron is moving to its lowest energy state, and the hole is also moving to its lowest energy state. So if you want to think about the electron as a bowling ball and the hole as a balloon, you're welcome to. Whatever mechanism helps you think through this process, use that as a crutch right now as we move forward. Always remember that in the system, these are electrons essentially moving down and filling up that hole, and that hole is moving in the opposite direction, much like the vacancy in a traffic jam. So again, thermalization losses can be described by both electrons and holes in our system, by both the rattling around of that electron in the conduction band and the settling of electrons here in the valence band as well, or the rising of that hole toward the valence band maximum and the settling of that electron toward the conduction band minimum. So a natural question is, how fast is this process? Can it be reversed? If we're losing all this energy due to the thermalization, can somehow we halt it and stop it from happening? There are people trying. It is a valiant fight. This plot right here represents the what's called the density of states. We're going to get to that in another lecture here, but I'm going to expose you to the rough concept right here. Y-axis is energy. So again, we have our valence band maximum and our conduction band minimum up there. X-axis here is representing time. So we're going from the excitation event, which occurs right at t = 0. 0 plus represents that this is on the positive side, moving time forward from the excitation event. So instantaneously after the excitation event, we had the equilibrium population of holes and of electrons inside of our semiconductor system. There weren't absolutely 0 electrons in the conduction band because of heat. There was enough thermal energy in our system to excite some of those electrons across, and that's why we had that small population of electrons there in holes down here, the holes they left behind. Now we had a photon coming in, high energy photon, that excited these electrons down here up there into the valence band, up into here in the valence band, right? And over time, this excited population will decay down to the conduction band minimum and valence band maximum, the electrons and the holes respectively. And over time, when I say over time, I'm referring to something in the range of 1 picosecond, 10 to the minus 12 seconds. That's like that, but faster, right? So we have a quick decay of these photoexcited carriers, and so extraction of that energy is going to be nearly impossible unless we do something very clever with our crystal to prevent that decay from happening. Somehow we suppress the phonons from being emitted at that frequency, at least, or at that energy. So there are a lot of people, clever people, working on this problem and trying to prevent the decay. The next challenge, of course, is extracting those so-called hot carriers, the excited carriers from your device, and keeping that energy when they're going into the metal. That's a whole other can of worms. So we have the time scales of thermalization, and this is why, at least from the perspective of your homework, we're going to treat thermalization losses as inevitable. As Harvard and MIT students, I would urge you to never consider anything as inevitable. If we understand the physics well enough, we can probably engineer a solution. But for now, let's consider this a reality, a loss mechanism. So if we start putting things together, if we put non-absorption, which we talked about last lecture, we actually ran some calculations back of the envelope and we calculated the thickness necessary to absorb 90% of the photons at a given wavelength. We also know how to calculate reflectance off of a front surface. And so we get this third point right here. We actually got it last class. And the fourth point right here, we intuitively understand now that if the photon comes in with more energy than the band gap, that excess energy is going to be lost due to thermalization. So now if we have the solar spectrum and we know the band gap of a semiconductor, we should be able to do a very cursory plot of the efficiency versus band gap versus energy of, So we have thermalization losses, the band gap is too small, and non-absorption losses, the band gap is too large. And let's just do an absurd thought experiment. If we say, okay, I'm really, really scared of thermalization losses, so I'm going to make the biggest band gap material I possibly can, I'm going to have a very low efficiency in my cell because I'm not absorbing any light. The solar cell will be transparent. If I'm scared of non-absorption losses, I say, okay, I'm going to make my band gap really, really, really tiny. I'm going to be losing a heck of a lot of energy due to thermalization, due to this loss mechanism right up here. And so there has to be some happy optimum somewhere between the two where we have the maximum potential efficiency of a solar cell device, given our solar spectrum. And we're going to walk through that right now. So approximating non-absorption losses, very first step. What we're going to do for our non-absorption losses is run a very quick approximation that any photon with energy, photon energy corresponding to the bandgap energy is going to be absorbed. So if our photon energy has, if the photon has a larger energy than the bandgap, it will be absorbed. If it has an energy less than the bandgap, it will not be absorbed. And that's what this plot right here is representing. We have wavelength right here, longer wavelength, lower energy, smaller wavelength, larger energy, and at some point we have the turn on of absorption of our device because we have a bandgap at that energy. And on the y-axis here, I've plotted EQE, which is external quantum efficiency. I've coined the term over here on the left-hand side. It's the efficiency at which free charge carriers are generated by an incident photon on the device. So one way to think about it is if I have an EQE of 100%, that means that for each photon that I throw at my solar cell device, I'm generating and collecting one free carrier from that device, one electron hole pair, if you will, from that device. So that's plotted right here. That makes intuitive sense. This is an approximation, though, and I wanted to take it one step further. Again, planting the flag right here, because we're going to come back to this and we're going to use this. But I wanted to go one level deeper into the trees for everyone else who wants some more advanced concepts. This is the reality of how quantum efficiency looks. Yes, we have a turn-on depending on the material that's involved. We have silicon, gallium arsenide, copper, indium gallium diselenide, amorphous silicon, dye-sensitized solar cells, organic solar cells, a variety of different materials right here. And they're different turn-on wavelengths right here. So we have wavelength, different energies. Some turn on at lower energies, others at higher energies. So this represents more or less the bandgap turn-on energy, more or less. It also has to do with the thickness, how well it absorbs light. At the shorter wavelength, though, instead of just having a QE of 1 going all the way out to X-ray territory, we have a turn off at some point. Why is that? Why in a real device would we? Yeah, go ahead.
Glass is absorbing.
We have glass absorbing on the front side. That's one real big reason. Yeah, do we have another idea? Yep, glass absorption is one real big one. There are other dead layers inside of a solar cell device in the near surface region that also absorb the light in some architectures. So yeah, so it's not a perfect QE spectrum that looks like that. But why don't we care? For the purposes of just this engineering approximation, why aren't we bothered by these photons that we're losing down there?
The percentage of the solar spectrum that falls in that region is small.
Absolutely. So what we're doing is an engineering approximation right here to get to a very first cursory efficiency calculation, neglecting things at the extremes. Too short wavelength because there's just not a whole lot of solar flux down there, and too long wavelength because, again, not a whole lot of solar flux right there. So we're going to be using, this approximation in our homeworks, and that will get us somewhat close. If we really want it to be true, instead of using a box function like this, an absorption box function, we would use an absorption spectrum that looks something more like that, right? We would use a true absorption spectrum. And then convolute that with the thickness of the device to calculate what fraction of photons at each energy is absorbed inside of my device. And that would give you a plot that looks something more like this. Instead of this box plot up here, it might give you a plot that looked something more like this. Right? So you'd have instead of just a sharp turn-on, if you had a 1 micron thick silicon wafer, and we calculated last class that we needed somewhere around 10 microns or 100 microns to absorb light well, if we reduce the thickness of the wafer to 1/10 or 1/100th of what's necessary to absorb light well, we don't see that sharp turn-on at the bandgap. We see rather a gradual turn-on of our silicon as we move to shorter and shorter wavelengths that are absorbed more and more efficiently by the device. So again, just wrapping our head around the basic concept that we're going to use for the purposes of our calculation, but again, some of the more fine structure, some of the more advanced concepts that come into play when we're doing more detailed calculations. Approximating thermalization losses now. We want to calculate the amount of energy lost, of incident sunlight lost due to thermalization, due to heat. And we're going to say here that if the photon energy is greater than the bandgap, then the photon energy is approximately the band gap plus thermalization. Another way to put it would be the thermalization is approximately the photon energy minus the band gap energy. So that's, I kind of wanted to hide all this down here. Forget this exists right now. Let's focus on that top part. So that's the easy way of thinking about it. We're going to be thinking about this in terms of just any photon coming into our device with a larger energy than the band gap is going to generate one electron hole pair and lose some energy due to thermalization. The reality is that for very high energy photons, say for example with photons with 3 times the band gap energy or more, you can have electron-electron interactions. So if you excite one electron to a very highly excited state, it can bounce around and in the process excite another electron across the band gap. That's the case when X-rays are incident on a piece of silicon, for instance. If you have a 10 kiloelectron volt, so 10,000 eV X-ray incident on a piece of silicon, you will generate approximately 3,000 electron hole pairs with that one X-ray, because that one X-ray is going to take an electron and excite it to a very highly excited state, and that's going to excite further electrons across the band gap as that photoexcited carrier decays, as it loses its energy and settles at the conduction band minimum. So we have what's called multiple exciton generation, sometimes referred to as multiple free carrier generation, in semiconductors as a hot topic because folks would like to take the ultraviolet portion of the spectrum, the high energy, short wavelength portion of the solar spectrum, and use it to excite multiple carriers, one photon exciting multiple carriers across the band gap. And so there's some work, or was some work, it was a hot topic for a while, it's kind of decayed a bit now. It comes in waves, it cycles, kind of like a plane wave. There is interest, I would say general interest in the field of how do you capture these higher energy photons and convert them in some usable way instead of just having thermalization loss, instead of just having heat. And then for really high energy photons, gosh, you can really get into some neat physics. I've given you a link and a cross section here. This is the electron cross section, or actually really what it is an atomic cross section. It's because of the electrons in the material, versus photon energy going from 10 eV out to 10 to the 11 eV, so very high photon energy. We're transiting from the, say, the visible spectrum over here deep into the infrared and then going into the X-ray and finally into the gamma ray regime. There you can have a number of interesting phenomena. You can even have electron hole or electron-positron pair generation with giga electron volt incident radiation or above. We're not going to even talk about this regime because the total amount of solar flux in that regime is really tiny compared to the visible. But it's a lot of interesting, fascinating physics. So I put it on here anyway, just to keep our approximation in focus. Right? So again, I'm kind of mixing the forest and the trees here to give you a sense of the complexity, but also to give you the tools necessary to do simple calculations. We're going to combine this simple approximation right here of the non-absorption losses. And we're going to say that any photon with energy less than the band gap doesn't get absorbed by our crystal. It's gone to us. And we're going to make the approximation that any photon with energy above it will have that excess energy lost due to thermalization. And we put those two things together, and one very convenient way of representing this is shown in a paper in 1980. Let me walk you through it. So this curve right here, this outermost curve, represents the solar spectrum, energy, versus number of photons. Right? So we have a